Imagine the Moon in its chaotic youth shortly after its violent birth from a collision between the young Earth and a Mars-sized protoplanet. It was a molten, seething sphere of rock, spinning far more rapidly than it does today, a wild, untamed world hurtling through space. As it orbited the Earth, our planet's immense gravity reached out across the 384,000 kilometers of space and took hold. The Moon, like any large celestial body, is not a perfect sphere. Earth's gravity pulling more strongly on the side of the Moon facing it than on the side facing away stretched its partner into a slight oblong shape, creating two subtle bulges of rock. One of these tidal bulges faced the Earth, and the other faced directly away. As the young, fast-spinning Moon rotated, these bulges were constantly being pulled out of alignment with the Earth. Our planet's gravity in turn relentlessly tugged them back, trying to keep them pointed directly toward and away from its center. This constant gravitational tug-of-war acted as a powerful brake. Imagine trying to spin a raw egg versus a hard-boiled one. The liquid interior of the raw egg sloshes around, creating internal friction that resists the spinning motion and slows it down. The early Moon, with its molten or partially molten interior, behaved in much the same way. The relentless pull of Earth's gravity on its tidal bulges created immense friction deep within the Moon's rocky mantle, generating heat and slowly, inexorably bleeding away its rotational energy. This process was not swift. It played out over hundreds of millions, perhaps even billions of years. It was a slow cosmic war of attrition, with Earth's gravity as the patient, unyielding victor. Second by second, millennium by millennium, the Moon's spin slowed. Its day, once perhaps only a few hours long, stretched longer and longer, the braking force of Earth's gravity never ceasing, never faltering. This process continued until the Moon reached a state of perfect, stable equilibrium. This equilibrium was achieved when the Moon's rotational period, the time it takes to spin once on its own axis, became exactly equal to its orbital period, the time it takes to complete one full orbit around the Earth. Today, both of these periods are 27.3 Earth days. The Moon spins once on its axis in the exact same amount of time it takes to circle our planet once. This perfect one-to-one resonance means that the same hemisphere is always eternally facing us. From our vantage point, it appears as though the Moon is not spinning at all, but this is an illusion born of our shared motion. The Moon is spinning, but its rotation is so perfectly synchronized with its orbit that it keeps one face locked in our direction, like a dancer who circles their partner while always keeping their eyes fixed upon them. This is the lowest energy state for the Earth-Moon system, a cosmic settling point where the gravitational stresses are minimized. It is not a unique phenomenon. Most of the major moons in our solar system are tidally locked to their parent planets. The giant moons of Jupiter and Saturn, the distant moons of Uranus and Neptune, all have succumbed to the same patient gravitational braking over the eons. Even the dwarf planet Pluto and its largest moon Charon are mutually tidally locked, forever facing each other in a frozen, silent embrace across the dark frontiers of the solar system. This tidal locking is almost but not quite perfect. Over the course of a lunar month, we can actually see slightly more than half of the Moon's surface. This is due to a subtle, gentle rocking and wobbling motion known as libration. One cause of this is the Moon's elliptical orbit. The Moon's path around the Earth is not a perfect circle, but a slight oval. According to Kepler's laws of planetary motion, the Moon moves slightly faster in its orbit when it is closer to the Earth, and slightly slower when it is farther away. Its rate of rotation, however, remains nearly constant. This mismatch between its orbital speed and its rotational speed allows us to peek just a little bit around the Moon's eastern and western edges at different points in its orbit, revealing slivers of the hidden terrain. Another form of libration is caused by the tilt of the Moon's axis. Just as the Earth's tilt gives us our seasons, the Moon's slight tilt allows us to see a little over its north and south poles at different times of the year. When you combine all these subtle librations, the result is that over time we can observe roughly 59% of the Moon's total surface. But the remaining 41%, the true far side, remains forever beyond our direct line of sight from Earth. It is a vast, hidden continent, a realm of permanent mystery that for all of human history existed only in the realm of imagination. Because no one could see it, the far side became a blank canvas for human speculation. Ancient civilizations who meticulously mapped the patterns of the near side and wove them into their mythologies and calendars could only guess at what lay beyond. For millennia, it was a place of pure conjecture. Some early thinkers, assuming a kind of cosmic symmetry, imagined that the far side was simply a mirror image of the near side, another patchwork of dark seas and bright highlands. Others, letting their imaginations run wild, envisioned a completely different world, a place of towering mountains, deep chasms, or perhaps even a secret sanctuary for life, shielded from the harsh glare of the Earth in the night sky. With the invention of the telescope in the 17th century, humanity's view of the near side was revolutionized. Galilei, pointing his rudimentary spyglass at the moon, was the first to see that it was not a smooth, ethereal orb, but a rugged, cratered world in its own right. Over the next 3 centuries, telescopes grew more powerful, and our maps of the near side became increasingly detailed. We gave names to its craters, its mountains, its vast, dark plains. We charted its features with a precision that would have astounded our ancestors. But no telescope, no matter how large or sophisticated, could defeat the fundamental physics of tidal locking. No instrument on Earth could bend light around the limb of the moon to reveal the secrets of its hidden hemisphere. The far side remained a perfect, absolute void on our maps, a stark white emptiness that taunted our curiosity. The development of photography in the 19th century allowed us to create permanent objective records of the near side, but it offered no new clues about the far side. The mystery endured a constant reminder of the limits of our perception, a silent challenge that seemed to mock our growing scientific prowess. To see the far side, to fill in that blank space on our maps, humanity would need more than just better telescopes. We would need to leave our world behind. We would need to develop a technology that had until the 20th century existed only in the pages of science fiction space travel. The obstacles were monumental. We needed rockets powerful enough to overcome Earth's immense gravitational pull guidance systems, precise enough to navigate across hundreds of thousands of kilometers of empty space, and communication systems robust enough to send and receive signals across those vast distances. These were challenges that pushed the very limits of engineering and physics. The dawn of the space age in the mid-20th century, ignited by the geopolitical rivalry of the Cold War, changed everything. The launch of the Soviet Union's Sputnik 1 in 1957 was a watershed moment, a signal that humanity was no longer bound to the surface of its home planet. The impossible was suddenly within reach. The race to the moon began in earnest, a competition driven as much by national pride as by scientific curiosity. But even with the advent of powerful rockets, observing the far side presented a unique and formidable challenge: communication. Any spacecraft orbiting over the far side of the moon would be completely blocked by the moon itself. There would be no direct line of sight to Earth. Imagine standing on one side of a mountain and trying to talk to someone on the other side. The mountain blocks your voice. In the same way, the entire body of the moon, thousands of kilometers of solid rock, would block any radio signals from a far-side probe. Any images, any data, any scientific measurements it collected would be trapped useless unless a solution could be found. This fundamental problem of communication led to the development of relay satellites, spacecraft placed in specific orbits that could catch a signal from a far-side probe and then bounce it back to Earth. Without such a system, any long-term meaningful exploration of the hidden hemisphere would be impossible. The first nation to solve this puzzle, to finally pierce the veil of the far side, was the Soviet Union. In October of 1959, just 2 years after Sputnik, they launched the Luna 3 spacecraft. Its mission was audacious: to fly to the moon, swing around its far side, photograph the hidden terrain, and transmit those images back to Earth. The technology was primitive by today's standards. The spacecraft carried a camera that used actual photographic film. In the harsh vacuum of space, an onboard automated system had to develop, fix, and dry this film. Then a tiny beam of light scanned the developed images line by line, converting the variations in brightness into an electrical signal that was beamed back across the void. The images that were received on Earth were crude, blurry, and streaked with static from the long and difficult transmission. But they were revolutionary. For the first time in human history, we were looking at the far side of the moon, and it was nothing like we had expected. The blurry photographs from Luna 3 revealed a landscape that was dramatically different from the familiar face of the near side. The most striking feature was the almost complete absence of the large, dark volcanic plains, the Maria, that are so prominent on the side facing Earth. Instead, the far side was a rugged, almost uniform expanse of bright, heavily cratered highlands. It was a world that had been battered and scarred by billions of years of impacts, a landscape that seemed older, more ancient, and far more violent than the one we knew. The far side was not a mirror image of the near side. It was its own distinct world, with its own unique geological character, hinting at a separate and profoundly different evolutionary history. These first ghostly images sparked a firestorm of excitement in the scientific community. They opened the door to a host of new questions, new theories, and new avenues of research. The blank space on our maps was finally beginning to be filled in, and the story it was starting to tell was one of asymmetry, of a world with two faces, each shaped by different forces over the vast expanse of deep time. Humanity's understanding of its closest cosmic companion was forever changed. The mystery of the far side was not solved. It had only just begun. The initial grainy photographs from Luna 3 were like a single tantalizing sentence from a book written in a language we were just beginning to understand. They offered a glimpse, a whisper of the story that the moon's far side had to tell, but they were far from a complete translation. They revealed a world of craters, but concealed the details of its composition, its history, and the deep geological forces that had sculpted its alien terrain. At the time, the National Aeronautics and Space Administration, or NASA, was a young and ambitious agency born from the urgency of the space race and fueled by a powerful mixture of scientific curiosity and national pride. The Soviet Union had achieved the first victory in the race to the moon's hidden hemisphere, but for NASA, the journey of lunar exploration was just beginning. The agency embarked on a series of methodical, increasingly sophisticated missions that would lay the groundwork for decades of scientific discovery and ultimately for humanity's first steps on another world. The early focus of these missions was necessarily on the near side of the moon. This was a matter of simple practicality. It was far easier to land a spacecraft and maintain communication on the side that was in constant view of Earth. The Surveyor program sent a series of robotic landers to make the first American soft landings on the lunar surface, testing the soil and sending back detailed images of the terrain. The lunar orbiter missions systematically photographed the near side with high-resolution cameras, creating a detailed atlas of potential landing sites for the upcoming Apollo program. These missions were crucial for ensuring the safety of future human explorers, but for scientists, the allure of the far side, the great unknown, remained a powerful magnet. The drive to explore this hidden realm was not just about satisfying curiosity. It was about answering some of the most fundamental questions about the moon and the history of our solar system. Was the heavily cratered far side truly older than the volcanically resurfaced near side? Did the two hemispheres experience different patterns of asteroid and comet impacts in the early chaotic days of the solar system? Did the far side contain unique minerals or geological structures that held the key to understanding the moon's violent formation and its subsequent evolution? These questions became the scientific rationale for future exploration, shaping the design of new missions and the development of new technologies. NASA's approach was a careful step-by-step ascent of a ladder of increasing technological complexity. First came the flyby missions like Luna 3, which offered brief but revolutionary glimpses of new territory. Next were the orbiter spacecraft that could circle the moon for extended periods, methodically mapping its entire surface in detail and gathering consistent data over time. The ultimate challenge was a soft landing, a mission that could place a robotic probe gently on the surface to collect samples, analyze the soil directly, and serve as a stationary scientific outpost. Each stage of this process required significant technological leaps. Navigation systems had to evolve from simple trajectory calculations to complex real-time adjustments. Imaging technology had to advance from blurry, low-resolution scans to high-definition digital photography. And for any mission targeting the far side, the problem of communication remained the most pressing and difficult hurdle to overcome. Without a reliable relay system, any spacecraft operating on the far side would be in a state of enforced radio silence, completely isolated from its controllers on Earth. The importance of communication satellites cannot be overstated. They are the invisible bridge that connects the hidden hemisphere to our own. Any long-term operation on the far side, whether it is a robotic rover exploring a crater or a future human habitat, is entirely dependent on a network of orbiting satellites. These satellites act as cosmic middlemen, catching faint signals from the lunar surface, amplifying them, and relaying them back to Earth. They also receive commands from mission control and transmit them down to the surface, allowing for two-way communication across the barrier of the Moon itself. Designing and deploying this kind of relay network is a complex orbital ballet requiring precise placement of satellites in stable orbits like the Earth-Moon Lagrange, points where the gravitational pull of the two bodies is balanced. It is a testament to human ingenuity that we have been able to overcome this fundamental physical barrier to create an artificial line of sight where nature provided none. The journey from those first blurry images to the detailed, comprehensive understanding we have today has been a long and challenging one, a story of persistence, innovation, and an unquenchable desire to explore the unknown. The far side is no longer a blank space on our maps. It is a rich and complex landscape, a geological archive filled with clues about the Moon's dramatic past. Its ancient cratered highlands are a preserved record of the late heavy bombardment, a violent period in the early solar system when the inner planets were pummeled by a storm of asteroids and comets. Its unique geological features like the colossal South Pole Aitken Basin offer a window deep into the Moon's crust and possibly even its mantle. And its radio-quiet environment, shielded from the constant chatter of human civilization on Earth, makes it a prime location for future radio telescopes. Instruments that could listen for the faint whispers of the early universe signals that are currently drowned out by our own electronic noise. It is remarkable to consider the arc of this story. For millennia, humanity stared up at a single unchanging face in the night sky, a familiar but ultimately limited view of our closest celestial companion. Now, we are able to map and study the Moon in its entirety, to see it not as a two-dimensional disk, but as a three-dimensional world with two profoundly different hemispheres. This leap in perspective was made possible by a convergence of scientific curiosity, technological innovation, and the political will to venture beyond the confines of our own planet. The journey to the far side of the Moon is more than just a story of exploration. It is a story about the expansion of human consciousness, about our species' ability to overcome the physical limitations of our senses, and to build a picture of reality that is far larger and more complex than what we can see with our own eyes. From the very first comparisons of the two hemispheres, scientists were struck by their stark and fundamental differences. The near side is defined by the Maria, those vast, dark, and relatively smooth plains of basaltic lava that were created by ancient volcanic eruptions. These Maria are lightly cratered, indicating that they are geologically younger than the surrounding terrain. The lava flows that formed them effectively paved over and erased the older impact scars. The far side, in dramatic contrast, is almost entirely composed of bright, rugged, and heavily cratered highlands. The Maria are few, small, and scattered. This dichotomy between a volcanically active near side and a relatively quiescent far side became the central puzzle of lunar geology. The leading theory to explain this asymmetry focuses on the thickness of the Moon's crust. Scientists now believe that the far side's crust is significantly thicker than the near side's. This thicker crust would have acted as a formidable barrier, making it much more difficult for molten magma from the moon's interior to reach the surface and form volcanic plains. The near side, with its thinner crust, was more easily fractured by large impacts, providing pathways for lava to flood the Great Basins and create the Maria. The discovery of this difference in crustal thickness was one of the most important revelations to come from the exploration of the far side. Subsequent missions using instruments like gravity gradiometers and laser altimeters have refined these measurements and confirmed the stark asymmetry in the moon's internal structure. This geological divide tells a story that begins with the moon's very formation. It suggests that as the primordial magma ocean of the young moon cooled and solidified, the crust formed unevenly, perhaps influenced by the gravitational pull of the Earth or the uneven distribution of heat-producing radioactive elements in its interior. The far side, in this sense, is a geological Rosetta Stone, a preserved remnant of the moon's earliest crust that holds the key to understanding its formation and its long divergent evolution. This story of discovery was built upon a foundation of breathtaking technological progress. Rocket engines became more powerful and efficient, capable of lifting heavier and more sophisticated spacecraft. Navigation systems evolved from simple radio tracking to complex autonomous systems that could guide a probe to a precise landing spot on an alien world. Communication technology advanced from the slow, noisy transmissions of the early space age to high-speed data links capable of sending back vast streams of scientific information in near real time. Power systems for these deep space probes also underwent a revolution, moving from short-lived chemical batteries to long-lasting solar panels, and for missions that needed to survive the long, cold lunar night, radioisotope thermoelectric generators that could provide a steady supply of power for years. The scientific instruments carried by these spacecraft grew increasingly precise and powerful. Simple cameras were joined by a host of other sensors. Spectrometers could identify the chemical composition of rocks and minerals from orbit by analyzing the light they reflect. Altimeters could map the topography of the surface with incredible accuracy, revealing the true scale of mountains and the depth of craters. Gravimeters could detect the subtle variations in the moon's gravitational field, providing clues about the structure of its hidden interior. All of these tools, working in concert, have allowed scientists to peel back the layers of the far side's mysteries to transform it from a land of speculation into a world of known geology. For future missions, especially those involving a long-term human or robotic presence, communication remains the most critical and challenging piece of the puzzle. Any outpost on the far side will require a dedicated network of relay satellites carefully positioned to maintain a constant link with Earth. Without this invisible infrastructure, a far side base would be isolated for long periods, unable to send back data or receive commands, a lonely outpost in a radio-silent wilderness. This relay system is as essential to the future of far-side exploration as the landers and rovers themselves. It is the lifeline that will connect the hidden hemisphere to humanity, the invisible bridge that will make long-term settlement possible. The importance of the far side extends beyond geology. Its unique environment, shielded from the radio noise of Earth, makes it perhaps the most valuable piece of real estate in the solar system for the science of radio astronomy. An observatory on the far side could detect the faint low-frequency signals from the cosmic dark ages, the period just after the Big Bang, before the first stars ignited. These signals, which hold the secrets of the universe's very first moments, are completely swamped by the radio interference from our own planet. The far side of the moon is the quietest place in the inner solar system, a natural laboratory for listening to the whispers of creation. As we look to a future of long-term lunar exploration, perhaps even human settlement, understanding the conditions on the far side, its radiation environment, its extreme temperatures, its unique surface properties, is crucial for ensuring the safety and sustainability of those missions. Every piece of data we gather, every image we take, brings that future a little closer to reality. transforming the once hidden face of the moon into a new frontier for human expansion. The study of the far side is a story that illuminates not just the moon itself, but our own place in the cosmos. It reveals the subtle, powerful interplay of gravity, the slow, relentless march of geological time, and the profound and beautiful asymmetry that can emerge from the chaotic processes of planetary formation. The hidden moon, once a symbol of the unknown, has become a monument to human curiosity, perseverance, and our unyielding desire to explore the darkness and bring back light. The human relationship with the moon began not with science, but with wonder. For countless generations long before the invention of telescopes or the language of physics, our ancestors looked up at the night sky and saw in that glowing silvery orb a source of magic and mystery. The moon was a deity, a divine chariot, a celestial clock that marked the passage of months and governed the rhythm of the tides. Ancient civilizations across the globe wove elaborate myths and stories around its changing phases, seeing in its cyclical journey a reflection of the great cycles of life, death, and rebirth. It was less an object to be studied and more a symbol to be revered, a powerful living presence in the cosmic theater. Yet even in those ancient times, the first seeds of a more scientific understanding were being sown. In the 5th century before the Common Era, the Greek philosopher Anaxagoras made a bold and revolutionary proposal. The moon, he argued, was not a god or a divine light, but a solid rocky world, much like the earth that shone only by reflecting the light of the sun. This was a radical departure from the mystical worldview of his time, a first tentative step toward seeing the cosmos not as a realm of supernatural forces, but as a physical system governed by natural laws. Aristotle, another giant of Greek philosophy, would later incorporate this idea into his comprehensive model of the universe. In his geocentric cosmos, the Earth sat motionless at the center, while the sun, the moon, and the planets traced perfect circular paths around it. While his model would ultimately be proven wrong, Aristotle's systematic approach, his emphasis on observation and logical deduction, laid the intellectual foundations for more than 1,000 years of astronomical thought. Slowly, painstakingly, the idea of the moon as a real physical place began to take root in the human imagination. And with that idea came another even more audacious one, the dream of flight, the ancient universal yearning to rise above the earth and touch the heavens. The myth of Icarus, who flew too close to the sun on wings of wax, is a timeless symbol of this desire. While these were not dreams of space travel, in a modern sense they revealed a deep primal longing to escape the bonds of gravity, a prelude to the far grander ambition of reaching other worlds. For centuries, however, this ambition remained purely in the realm of fantasy. The laws of physics were a mystery, and journeys to the moon belonged to poets and storytellers, not to engineers. Everything changed in the 17th century as the scientific revolution began to illuminate the universe with the bright, clear light of reason and evidence. The invention of the telescope and its masterful application by Galileo Galilei transformed our understanding of the moon almost overnight. Galileo's observations revealed a world of stunning complexity and detail, rugged mountains, deep valleys, and countless craters. He proved once and for all that the moon was not a smooth, ethereal sphere, but a world in its own right, with its own unique geography. He even performed a remarkable early experiment in planetary science, measuring the heights of lunar mountains by analyzing the length of the shadows they cast. The moon had become a real, tangible place, a destination that was no longer just a subject of mystical reverence, but of scientific inquiry, and for the first time of imaginative exploration. Fueled by this new scientific insight, a new genre of literature was born. Writers began to envision in a way that was more than just pure fantasy how humans might one day travel to the moon. In the mid-1600s, the French writer Cyrano de Bergerac penned a comical history of a journey to the moon, imagining a traveler lifted by bottles of evaporating dew or propelled by firecracker-powered rockets. Around the same time, the English bishop Francis Godwin published a tale of a hero who journeys to the moon in a chariot pulled by trained wild geese. While these stories were fantastical, they were extraordinary in that they began to grapple, however playfully, with the real physical challenges of space travel. They speculated about the nature of gravity, the need for breathable air, and the kind of societies that might exist on another world. They were planting the seeds of scientific thought within the fertile ground of fiction. By the 18th and 19th centuries, this blending of science and imagination had blossomed into the new genre of science fiction. The French novelist Jules Verne, writing in the 1860s, became one of its greatest masters. His novel, From the Earth to the Moon, imagined a trio of adventurers launched to the moon inside a giant projectile fired from a colossal cannon. Though the physics of such a launch would be unsurvivable, Verne went to extraordinary lengths to ground his story in the science of his day. He meticulously calculated trajectories, velocities, and escape velocities, and he gave his readers a thrilling and scientifically plausible description of what it would be like to experience weightlessness and to see the Earth from space. Meanwhile, the English author H.G. Wells, in his 1901 novel The First Men in the Moon, took a different approach, imagining a new material called cavorite that could negate the force of gravity, allowing for a more controlled journey. Wells also populated the moon with a complex and ancient alien civilization, using his story to explore sociological and philosophical themes, blending scientific curiosity with a deep inquiry into the nature of intelligence and society. Together, these literary works, and many others like them, sparked a widespread public fascination with space travel. They bridged the gap between fantasy and scientific possibility, inspiring generations of future scientists and engineers to look up at the moon not as a distant mystical light, but as a destination, a tangible goal that might one day be reached by human hands. The real seeds of space travel, however, were not planted in the pages of fiction, but in the minds of a few extraordinary and visionary thinkers in the late 19th and early 20th centuries. These pioneers of rocketry often worked in isolation, far from the scientific mainstream, facing skepticism and even ridicule from their contemporaries. One of the earliest and most profound of these visionaries was the Russian schoolteacher and self-taught scientist Konstantin Tsiolkovsky. Working in the late 1800s and early 1900s, Tsiolkovsky was the first to lay out the fundamental theoretical principles of rocketry. He devised what is now known as the Tsiolkovsky rocket equation, a mathematical formula that describes how a rocket's velocity changes as it expels mass. This simple but powerful equation revealed a fundamental truth: to achieve the high velocities needed for spaceflight, rockets would need to be incredibly efficient with high-speed exhaust and a very large ratio of fuel to total mass. Tsiolkovsky was a champion of liquid-fueled rockets, recognizing that they could provide far more power and control than the solid-fueled rockets of his day. He was the first to imagine multi-stage rockets, understanding that by jettisoning empty fuel tanks and engines during flight, a rocket could shed mass and achieve much higher speeds. He even envisioned the use of liquid oxygen and liquid hydrogen as propellants, a combination that remains one of the most powerful and efficient choices for modern rockets. But Tsiolkovsky was more than just a brilliant theorist. He was a philosopher and a dreamer who saw humanity's future not just on Earth, but among the stars. He imagined space stations, lunar bases, and the eventual colonization of the entire solar system. While his work was little known outside of Russia during his lifetime, he laid the theoretical groundwork upon which all of modern astronautics is built. Meanwhile, across the Atlantic, the American physicist Robert Goddard was pursuing his own revolutionary ideas. Often ridiculed by the press for his seemingly outlandish dream of space travel, Goddard quietly and meticulously conducted a series of groundbreaking experiments. In 1926, he achieved a historic milestone, the launch of the world's first liquid-fueled rocket. Though the flight was short and the altitude was modest, it was a profound proof of concept. It demonstrated that liquid propellant rockets could work in practice, not just in theory. Goddard spent the rest of his life refining his designs, patenting innovations like gyroscopic guidance systems and multi-stage designs, bridging the crucial gap between Tsiolkovsky's elegant equations and the practical hands-on engineering needed to turn theory into reality. In Germany, another towering figure, Hermann Oberth, was independently developing his own theories of rocketry. His 1923 book, The Rocket into Interplanetary Space, was a detailed and rigorous exploration of the physics and mathematics of spaceflight. Oberth's work inspired a generation of German engineers, including a young Werner von Braun, who would go on to play a decisive role in both the development of military rocketry and later the American space program. Together, Tsiolkovsky, Goddard, and Oberth are remembered as the fathers of rocketry. Though they worked largely independently, their ideas converged to form the holy trinity of modern astronautics. They showed that escaping Earth's gravity was not just a dream, but an achievable engineering goal. The brutal reality of the Second World War tragically accelerated the development of this technology. Under the leadership of Werner von Braun, Germany developed the V-2 rocket, the first large-scale liquid-fueled ballistic missile. Though it was designed as a weapon of war, the V-2 was a remarkable technological achievement, a machine capable of reaching the very edge of space. After the war, both the United States and the Soviet Union eagerly recruited German rocket engineers and brought V-2 technology into their own nascent missile programs, gaining a crucial head start in the arms race that would soon evolve into the space race. The Cold War added a powerful new impetus to the dream of space travel. The fierce ideological and technological rivalry between the United States and the Soviet Union transformed space into a new arena for competition, a stage upon which each nation could demonstrate its superiority. When the Soviet Union launched Sputnik 1 in October of 1957, the world's first artificial satellite, it sent a shockwave of urgency and anxiety through the United States. The launch was a stunning demonstration of Soviet technical prowess, and it sparked a determined effort in America to catch up and surpass its rival. This urgency led directly to the creation of NASA in 1958, a new civilian agency that consolidated America's scattered space efforts under a single unified banner. The mission was clear: to close the gap with the Soviets, to put a human in orbit, and as the ultimate goal, to land a human on the moon. The space race transformed the isolated theories of the early pioneers into a massive coordinated national endeavor involving hundreds of thousands of scientists, engineers, and technicians. Public imagination, already primed by decades of science fiction, was now fully captivated by the real-life drama of space exploration. The moon. Once the realm of gods and dreams, had become a tangible destination, a national goal backed by immense resources and political will. The leap from imagination to reality was powered by a potent combination of scientific curiosity, engineering ingenuity, and geopolitical competition. A convergence of forces that would, in just a few short years, turn humanity's ancient vision of the stars into a breathtaking reality. Out of this extraordinary period of human history, the very concept of the astronaut, the star sailor, was born, forever changing our understanding of who we are and our place in the universe. For all of human history, the far side of the moon was a perfect secret, a hidden world guarded by the unyielding laws of celestial mechanics. From our vantage point on Earth, we are bound to a single perspective, forever watching one half of our celestial partner, while the other remains cloaked in mystery. This is the consequence of tidal locking, the gravitational embrace that has synchronized the moon's rotation with its orbit, ensuring that the same hemisphere always faces us. To see the other side, to finally gaze upon the terrain that had remained unseen for eons, required a monumental leap, a journey that would take us beyond the confines of Earth's atmosphere and across the vast emptiness of space. The mid-20th century, a time of intense geopolitical rivalry between the United States and the Soviet Union, became the unlikely crucible for this new age of exploration. The space race was on a fierce competition in which each nation poured immense resources into developing the technologies that would allow them to achieve new milestones in space before the other. It was the Soviet Union with its early lead in powerful rocketry that would be the first to pierce the veil of the far side, providing humanity with its first ghostly glimpses of a world no one had ever seen before. This historic achievement was accomplished by a small, unassuming robotic probe named Luna 3. Launched in October of 1959, just over 2 years after the world-changing debut of Sputnik 1, Luna 3's mission was as daring as it was ambitious. Its goal was not just to reach the moon, but to perform a complex cosmic maneuver to fly around the unseen side, capture photographs of the hidden landscape, and successfully transmit those images back to Earth across hundreds of thousands of kilometers of space. The spacecraft itself was a marvel of engineering, for its time a testament to the ingenuity of its designers working at the very dawn of the space age. Shaped like a tapered cylinder, Luna 3 was equipped with solar cells for power antennas for communication and a specially designed imaging system that was both revolutionary and remarkably complex. The cameras it carried were primitive by today's digital standards. They used traditional photographic film, which had to be protected from the harsh radiation and extreme temperatures of space. Perhaps the most remarkable part of the system was its onboard automated film processing laboratory. While hurtling through the void, the spacecraft had to develop, fix, and dry the photographic film, a delicate chemical process that had never before been attempted in such a remote and hostile environment. Once the film was developed, the images had to be converted into a signal that could be transmitted back to Earth. This was achieved using a technique similar to early television broadcasting. A tiny beam of light scanned the developed film line by line, reading the variations in brightness and shadow. These variations were then translated into an electrical signal, which was broadcast back to Earth via radio waves. The process was slow and prone to interference, resulting in images that were often blurry and streaked with noise. But it represented the absolute cutting edge of remote sensing and long-distance communication technology in the late 1950s. Receiving these faint signals on Earth required enormous ground-based antennas and sophisticated processing equipment to reconstruct even the most basic details of the lunar surface. The trajectory of Luna 3 was also a masterpiece of early space navigation. Instead of entering a stable orbit around the moon, the spacecraft was designed for a circumlunar flyby. It was launched on a path that took it directly toward the moon, using the moon's own gravity to swing it around the far side before returning on a long looping path back toward Earth. This clever use of a gravitational assist allowed the spacecraft to achieve its mission without needing to carry the heavy fuel load required for major orbital maneuvers. On the 7th day of October 1959, Luna 3 swung around the far side of the moon, and its cameras began their historic work. As the spacecraft transmitted its precious cargo of images back to Earth, the world held its breath. The pictures that came back were far from perfect. They were low-resolution, grainy, and marred by the static of their long journey. Yet they were breathtaking. For the first time, humanity was seeing the other side. The initial photographs revealed a world that was profoundly and shockingly different from the familiar near side. The most immediate and striking feature was the near-total absence of the large dark plains, the Maria that give the near side its distinctive man-in-the-moon appearance. Instead, the far side was a rugged, almost unbroken expanse of bright, heavily cratered terrain. It was a landscape that spoke of a more ancient and violent history, a surface that had been relentlessly battered by impacts and had not been resurfaced by the vast lava flows that had smoothed over large portions of the near side. Only a few small, irregular dark patches could be seen, which would later be given names like Mare Moscoviense, the Moscow Sea. This rugged primordial landscape suggested that the far side had a fundamentally different geological history from the near side. The sheer density of craters implied an older, more stable surface, one that had preserved the scars of the early solar system's intense bombardment. These first images hinted at a deep asymmetry in the moon's structure, a fundamental difference in the thickness and composition of its crust between the two hemispheres. Scientists immediately began to speculate that the thicker crust of the far side had prevented magma from reaching the surface, explaining the absence of large Maria. This hypothesis, born from those first blurry images, would later be confirmed by more advanced missions. The Luna 3 mission also began the process of naming the features of this previously unknown world. The Soviet Union, in honor of its achievement, gave Russian names to many of the newly discovered craters and basins. The most prominent crater was named Tsiolkovsky, in honor of the great Russian pioneer of rocketry, whose theoretical work had made such a mission possible. For the first time, the blank space on our lunar maps began to be filled with names, with features with a sense of place. The achievement of Luna 3 was far more than a scientific milestone. For the Soviet Union, it was a stunning victory in the Cold War space race, another powerful demonstration of their technological leadership. For the public around the world, it was a moment of pure wonder. The moon, which had always been a distant and enigmatic object, suddenly felt more tangible, more real, and yet even more alien. The grainy photographs from Luna 3 ignited the public imagination and fueled the curiosity of scientists, confirming in the most powerful way possible that humanity had finally taken its first steps beyond the cradle of Earth. The data from Luna 3 proved to be invaluable for planning all future lunar missions, both Soviet and American. For the United States and its newly formed NASA, the images were a treasure trove of intelligence, highlighting the importance of mapping and studying the far side, not just the familiar hemisphere that had been the focus of all previous astronomy. Luna 3's success, though a Soviet triumph, offered crucial lessons in deep space navigation, remote imaging, and long-distance communication that would be studied and adapted by engineers around the world. Beyond its political and practical impact, the mission offered profound scientific insights. It was the first clear observational evidence of the consequences of tidal locking. By revealing the stark contrast between the two hemispheres, the images illustrated how Earth's gravity had not only synchronized the moon's rotation, but had also shaped its geology in profoundly uneven ways. The far side was not just the other side. It was a different world sculpted over billions of years by a different set of geological rules. Those first blurry photographs became more than just images. They were windows into a hidden landscape, the first definitive proof that the moon was an asymmetrical world. This revelation sparked decades of scientific debate and research, leading to new theories about the moon's formation from a giant impact and the subsequent uneven cooling of its magma ocean. The thicker crust of the far side, the leading hypothesis to explain its appearance, may have been a consequence of this violent birth, with the debris from the impact coalescing unevenly to form a world with two distinct faces. The technological achievements of Luna 3 were equally remarkable for their time. In the 1950s, sending a spacecraft to the moon, having it successfully operate a complex photographic and development system in the vacuum of space, and then transmitting those images back across hundreds of thousands of kilometers was an engineering feat of the highest order. Every aspect of the mission, from the reliability of its components to the precision of its trajectory, offered lessons that would inform the design of all subsequent robotic and eventually human space missions. Luna 3's triumph was not just about bringing back the first pictures. It was a proof of concept for the entire enterprise of robotic deep space exploration. It was a small step for a small spacecraft, but it was a giant leap for humanity's understanding of its place in the cosmos. The moon's hidden side was no longer a complete mystery. Its shadowed landscapes, once entirely unknown, had begun to emerge from the darkness. Blurry at first, but unmistakably real. Humanity had taken its first tentative look at a world that had long been just beyond our reach, and in doing so had opened the door to a universe of discoveries yet to come. The middle of the 20th century was defined by the tense ideological standoff of the Cold War, a rivalry between the United States and the Soviet Union that played out not just in politics and proxy wars, but in a new high-stakes arena, the vast uncharted territory of outer space. The spark that ignited America's full-scale commitment to this new frontier came on a crisp autumn day in October of 1957. On that day, the Soviet Union launched Sputnik 1, the world's first artificial satellite. This small, beeping metallic sphere circling the globe every 96 minutes was far more than a technological curiosity. It was a stunning demonstration of Soviet scientific and military power, and it sent a profound shockwave of anxiety and determination across the United States. The Sputnik crisis, as it came to be known, made it painfully clear that America could no longer afford to be complacent in this new cosmic race. Before Sputnik, space-related research in the United States was a fragmented and uncoordinated affair. Various branches of the military were developing their own rocket technologies, primarily for ballistic missiles. Civilian research was led by the National Advisory Committee for Aeronautics, or NACA, an agency focused primarily on aviation. There was no single unified national effort dedicated to the peaceful scientific exploration of space. The success of Sputnik made it obvious that a coordinated, centralized approach was essential. Recognizing this strategic and scientific urgency, President Dwight D. Eisenhower acted decisively. In July of 1958, he signed the National Aeronautics and Space Act, creating a new civilian agency with a clear and ambitious mission to organize and conduct America's aeronautical and space activities for the benefit of all humanity. This new agency was NASA. It was built on the solid foundation of NACA, inheriting its experienced engineers, its research facilities, and its decades of expertise in aerospace technology. NASA also absorbed other key research organizations like the Jet Propulsion Laboratory, consolidating America's talent and resources under a single powerful banner. The agency was designed to be agile and ambitious, capable of managing the massive complex missions that would be required to compete with the Soviets and push the boundaries of human exploration. Its goals were not modest. NASA quickly moved from launching satellites to the far more audacious goal of putting humans in space and ultimately sending them to the moon. This ambition was formalized in 1961 when President John F. Kennedy issued a bold and historic challenge to land a man on the moon and return him safely to the Earth before the end of the decade. This clear, daring goal galvanized the nation and set NASA on an accelerated and unprecedented path of technological development. But before humans could walk on the moon, a vast amount of information was needed about the lunar environment. NASA's early robotic missions, the precursors to Apollo, were designed to be the scouts, the trailblazers that would map the terrain, study the geology, and provide the critical intelligence needed to make human landings possible and safe. The first of these programs was Ranger. Launched in the early to mid-1960s, the Ranger spacecraft had a simple but dramatic mission to fly directly toward the moon and transmit high-resolution television images back to Earth in the final moments before they intentionally crashed onto the surface. The early Ranger missions were a painful lesson in the unforgiving nature of space exploration. Many of them failed due to technical setbacks, from power system failures to instruments that refused to function. But each failure was a valuable learning experience, helping engineers to refine their designs and perfect their procedures. Perseverance finally paid off with Ranger 7 in July of 1964. As the spacecraft hurtled toward its impact site in what would later be named Mare Cognitum, it transmitted more than 4,300 stunning high-resolution images. These pictures revealed the lunar surface in breathtaking detail, showing craters as small as a meter across. They provided the first conclusive evidence that the moon's surface was solid and firm, not covered in a deep layer of soft dust that could swallow a lander, which had been a major concern for mission planners. Building on the success of the Ranger impactors, NASA then launched the Surveyor program, a series of missions designed to achieve an even more ambitious goal, a soft landing. The Surveyor spacecraft were sophisticated robotic laboratories equipped with retro rockets to slow their descent and legs to cushion their touchdown. They carried television cameras to provide panoramic and close-up views of their landing sites, as well as instruments to analyze the lunar soil. Surveyor 1 made the first successful American soft landing on the moon in June of 1966, a historic triumph that proved NASA had mastered the complex art of landing a spacecraft on another celestial body. Over the next 2 years, 5 of the 7 Surveyor missions successfully touched down, sending back a wealth of data. They photographed the landscape, dug small trenches in the soil with robotic scoops to test its strength, and even carried alpha scattering instruments that made the first direct chemical analysis of the lunar surface, confirming that the dark maria were made of basaltic rock, similar to volcanic rocks on Earth. The data from the Surveyor missions was absolutely essential for the design of the Apollo lunar module and for the training of the astronauts who would one day walk on the Moon. It provided the ground truth, the direct hands-on knowledge of the lunar environment that no orbital mission could provide. In parallel with Ranger and Surveyor, NASA also launched the Lunar Orbiter program. The 5 Lunar Orbiter spacecraft, launched between 1966 and 1967, were designed to create a comprehensive high-resolution photographic atlas of the entire Moon, including the mysterious far side. Their primary goal was to scout and certify safe and scientifically interesting landing sites for the Apollo missions. The orbiters produced stunning detailed images that revealed the intricate topography of craters, mountains, and rills across the entire lunar surface. Their mapping of the far side provided a far clearer and more detailed picture than the early Luna 3 images, confirming its heavily cratered nature and the stark scarcity of Maria. Together, these 3 robotic programs, Ranger, Surveyor, and Lunar Orbiter, were the essential precursors to Apollo. They were the eyes, the hands, and the map makers that went before transforming the Moon from a distant object of study into a known, tangible world. They provided the indispensable foundation of knowledge upon which the daring Apollo program and humanity's first steps on another world would be built. The Apollo program was more than a series of missions. It was a human saga, a story of courage, ingenuity, and the unyielding desire to explore. And while its ultimate triumph was the landing of humans on the near side of the Moon, every journey to our celestial neighbor also provided a rare and privileged opportunity, a direct human view of the hidden hemisphere. As the Apollo astronauts circled the Moon, they became the first people in history to gaze upon the far side with their own eyes, supplementing the cold objective data of robotic probes with the irreplaceable perspective of human consciousness. The first of these journeys was Apollo 8. Launched in December of 1968, it was a bold and audacious mission. In a daring change of plans, NASA sent the crew of Frank Borman, Jim Lovell, and William Anders not just into Earth orbit, but on a direct trajectory to the Moon. Their mission was to be the first humans to orbit the Moon, a crucial dress rehearsal for a future landing. For the first time in history, human eyes would see the Earth as a whole planet, and for the first time they would see the far side of the Moon. As their spacecraft passed behind the lunar limb, all communication with Earth was cut off. For those tense minutes of radio silence, the crew was more alone than any human had ever been, truly isolated in the vastness of space. And then unfolding before them was the hidden landscape. Their first impressions, broadcast back to Earth when communication was re-established, confirmed what the robotic probes had shown, but with a new and powerful human dimension. They described a world that was utterly alien, a vast, desolate, and forbidding expanse. William Anders famously described it as looking like a pile of dirty sand. It was a rugged, monochrome world, pockmarked with craters upon craters, a testament to billions of years of relentless cosmic bombardment. Unlike the grainy images of robotic cameras, the human eye could perceive depth, texture, and scale in a way that conveyed the overwhelming and lonely grandeur of this hidden world. It was on this historic mission that one of the most iconic photographs in human history was taken. As the Apollo 8 spacecraft emerged from behind the Moon, the crew witnessed a sight that no one had ever seen before the Earth, a beautiful, fragile blue and white marble rising above the stark gray cratered lunar horizon. The Earthrise photograph captured a profound moment of cognitive shift for humanity, a new perspective on our own planet as a small, precious, and interconnected world. And it was a perspective that was made possible only by the journey to the far side of the Moon. Apollo 10 followed in May of 1969, a full dress rehearsal for the lunar landing. The crew of Thomas Stafford, John Young, and Eugene Cernan took the lunar module nicknamed Snoopy down to within 50,000 feet of the lunar surface, scouting the landing site for Apollo 11. During their 31 orbits of the Moon, they too had multiple opportunities to observe and photograph the far side, confirming its uniformly ancient and cratered character. And then came Apollo 11, the historic mission that would finally fulfill President Kennedy's challenge. While Neil Armstrong and Buzz Aldrin descended to the surface in the lunar module, Eagle Michael Collins remained alone in orbit aboard the command module, Columbia. For nearly a full day, Collins circled the Moon, passing repeatedly over the far side. His experience was one of profound solitude. He later described the feeling not as loneliness, but as a sense of awareness and connection to the universe. As he passed over the hidden hemisphere, cut off from all contact with humanity, he described a sense of peace, a feeling of being at one with the silent ancient landscape below. His observations, like those of the crews before him, reinforced the stark dichotomy between the two lunar faces. Subsequent Apollo missions continued to expand our knowledge of the far side. While the primary goal of these missions was the detailed scientific exploration of various landing sites on the near side, the orbital phases of each journey provided new opportunities for observation and data collection. The later Apollo missions, starting with Apollo 15, were equipped with a sophisticated suite of scientific instruments in the service module. These instruments, which included high-resolution mapping cameras, laser altimeters, and spectrometers, systematically collected data not just of the landing sites, but of large swaths of the entire lunar surface, including the far side. But even with this advanced robotic instrumentation, the first-hand impressions of the astronauts remained invaluable. They could provide a context, a sense of scale, and a uniquely human interpretation that complemented the raw data. They described the subtle variations in color and texture of the far side soil, the dramatic play of light and shadow across its rugged terrain, and the overwhelming sense of ancient time that was etched into its battered surface. A recurring and defining feature of every Apollo lunar mission was the period of communication blackout. Each time the spacecraft passed over the far side, radio signals to and from Earth were blocked by the body of the Moon. These periods of enforced radio silence, lasting for about 45 minutes on each orbit, became a powerful symbol of the astronauts' isolation and self-reliance. Just before losing signal, mission control would give a final go, and the crew would be on their own, relying solely on their training, their instruments, and each other until they emerged from behind the Moon and contact was re-established. For the command module pilots who remained in orbit alone, these periods of silence were a time of profound introspection, a unique opportunity to experience a kind of solitude that was unprecedented in human history. Even the near disaster of Apollo 13 offered a dramatic and unplanned encounter with the far side. After an explosion crippled their spacecraft, the crew was forced to use the Moon's gravity to sling them back toward Earth on a free return trajectory. As they passed behind the Moon, their already tenuous link with mission control was severed. What was normally a routine period of radio silence became a tense, anxiety-filled ordeal as they silently circled the hidden hemisphere in their damaged craft, unsure if they would ever make it home. Their journey was a stark and powerful reminder of the unforgiving nature of the far side, a place where there is no help, no communication, no direct line back to the safety of Earth. The sum of all these human observations from the Apollo missions dramatically expanded our understanding of the far side of the Moon. The astronauts' accounts added a rich human dimension to the precise measurements of robotic probes. They consistently reinforced the scientific conclusion that the far side was fundamentally different from the near side, older, more heavily cratered, and lacking the extensive volcanic resurfacing that had shaped the Earth-facing hemisphere. These observations helped to solidify the theories of the Moon's asymmetrical crust and its divergent geological history. Slowly but surely, through the combined efforts of robotic scouts and human explorers, the far side, once a realm of pure mystery, was revealing its secrets, enriching our understanding of our closest celestial neighbor, and forever changing our perspective on our own place in the cosmos. The legacy of their journeys continues to shape our knowledge of the Moon, transforming what was once a hidden, shadowed world into a well-studied and vividly imagined landscape. The surface of the Moon is a library of cosmic history, its pages written in the language of craters. Each circular depression is the scar of a violent collision, a silent witness to the chaotic and formative years of our solar system. These impact features range in size from microscopic pits etched by tiny dust particles to colossal basins hundreds of kilometers across the remnants of ancient planet-shattering impacts. And among them all, one stands alone in its sheer scale and scientific significance: the South Pole Aitken Basin. This enormous ancient structure, located almost entirely on the Moon's far side, is not just the largest and deepest confirmed impact basin on the Moon. It is one of the largest and oldest known impact features in the entire solar system. Its immense size, its hidden location, and the scientific secrets it holds have made it a prime target for exploration, a place that may hold the key to understanding the very formation of the Moon and the violent bombardment that shaped all the rocky worlds in our solar system. The existence of this giant basin was not revealed in a single sudden discovery. Its reality emerged slowly, piece by piece, as successive robotic missions provided increasingly detailed views of the far side. The first hints came from those blurry, low-resolution images from the Soviet Luna 3 probe in 1959, which showed a vast, heavily cratered terrain. In the mid-1960s, NASA's Lunar Orbiter program returned much higher-resolution photographs, allowing scientists to begin mapping a vast, subtle topographic depression on the far side, gradually revealing the colossal scale of what would come to be known as the South Pole Aitken Basin. Later images from the Apollo missions provided even more detail, but the basin's full extent remained difficult to grasp, partly because it is so ancient and has been battered by countless subsequent impacts, and partly because the low angle of sunlight near the lunar poles casts long, obscuring shadows. The basin's name reflects its location. It is centered near the Moon's south pole and extends northward all the way to the crater Aitken. Its dimensions are staggering. It stretches for roughly 2,500 kilometers or 1,550 miles from rim to rim. That is roughly the distance from New York City to Dallas, Texas. Its depth is equally impressive, varying from 6 to 8 kilometers or 4 to 5 miles from its rim to its floor. It is a truly monumental excavation of the lunar crust, a scar of unimaginable proportions. The age of the South Pole Aitken Basin adds to its profound scientific importance. Scientists estimate that it was formed very early in the Moon's history, sometime between 4.2 and 4.3 billion years ago. This places its formation during the hypothesized period known as the Late Heavy Bombardment, a time when the early solar system was a cosmic shooting gallery with a vast number of asteroids and comets raining down on the inner planets. As one of the oldest and largest surviving relics of this violent era, the basin is a key geological marker, a reference point for understanding the history of the entire solar system. NASA's exploration efforts have been crucial in uncovering the secrets of this giant basin. While early missions provided photographic evidence, more advanced instruments were needed to understand its composition and internal structure. In the 1990s, the Galileo spacecraft on its way to Jupiter and the Clementine mission provided multispectral and topographic data that began to reveal the basin's unique mineral makeup. A particularly important mission was NASA's Lunar Prospector, launched in 1998. Its gamma-ray spectrometer mapped the elemental composition of the lunar surface and revealed that the floor of the South Pole Aitken Basin had unusual concentrations of iron and titanium. This was a tantalizing clue suggesting that the colossal impact that formed the basin had dug so deep that it had excavated material from the Moon's mantle, the layer that lies beneath the crust. The most detailed information about the basin has come from NASA's Lunar Reconnaissance Orbiter, or LRO, which has been orbiting the Moon since 2009. LRO's suite of advanced instruments has revolutionized our understanding of this ancient feature. Its Lunar Orbiter Laser Altimeter, or LOLA, has created incredibly precise three-dimensional maps of the basin's topography, revealing its true depth and the complex structure of its floor and rim. Its diviner instrument has measured the surface temperature, providing clues about the composition of the rocks. These modern detailed maps have consistently shown that the floor of the South Pole Aitken Basin contains rocks that are rich in iron and magnesium elements that are typically found in the lunar mantle. This strongly supports the hypothesis that the impact was so massive, so powerful, that it punched completely through the Moon's crust, exposing material from its deep interior. For scientists, this is an extraordinary opportunity. The basin acts as a natural drill hole, giving us a window into the Moon's mantle without having to physically drill down through tens of kilometers of rock. The leading theory for the basin's formation proposes that it was created by the collision of an enormous asteroid or comet, perhaps 200 kilometers across, traveling at incredible speed. The energy released in this event would have been almost unimaginable, far surpassing any explosion in recorded human history. Such a collision would have instantly vaporized vast amounts of rock and hurled enormous quantities of debris across the lunar surface and into space. The crater formed by this impact was so large that its rim would have immediately collapsed inward, forming the multi-ringed structure that is characteristic of such giant basins. Over the billions of years that followed, this structure has been softened and degraded by subsequent impacts, but its fundamental outline remains. One of the most profound effects of the South Pole Aitken impact is that it significantly thinned the lunar crust beneath the basin floor. This thinning, combined with the immense heat of the impact, might have been expected to trigger widespread volcanic activity, creating a vast mare basin similar to those on the near side. And yet the basin does not contain the extensive flood basalts that are common in near-side basins. While there are some small patchy mare deposits, they are far less voluminous than those in basins like Mare Imbrium. This has sparked a lively scientific debate. Perhaps the impact occurred at a time when the Moon's interior was not yet hot enough to produce large-scale volcanism. Or perhaps the mantle rocks exposed by the impact were not of the right composition to melt easily and form widespread lava flows. This puzzle is central to the scientific importance of the basin. If the rocks on its floor are indeed pristine mantle material, they hold the key to understanding the Moon's deep interior. Researchers are particularly eager to find and analyze samples of minerals like olivine and pyroxene, which are common in Earth's mantle and are thought to make up the bulk of the Moon's mantle as well. Data from LRO and other orbiters already suggest that these minerals are present in the basin, but analyzing actual samples would provide the definitive proof. Understanding the composition of the mantle is crucial for learning about the Moon's thermal history, its ancient magnetic field, and the process of differentiation by which it separated into a core mantle and crust. The South Pole Aitken impact may also hold the key to understanding the fundamental asymmetry between the Moon's near and far sides. The enormous energy released in the impact and the massive redistribution of mass would have had a profound effect on the Moon's gravitational field and its internal thermal structure. Some models suggest that the impact could have shifted the Moon's center of mass or altered the patterns of heat flow within its interior. These changes may have contributed to the differences in crustal thickness and the uneven distribution of volcanism between the two hemispheres. The scientific importance of the basin is vast. It is a rare window into the violent conditions of the early solar system. It provides unparalleled access to the Moon's deep interior, and because of its location at the South Pole, it is a region of immense interest for future human exploration. The basin's geography means that many of the deep, permanently shadowed craters that are thought to contain water ice lie within its vast expanse. This discovery is crucial for the future of human space exploration. Water ice can be harvested and converted into drinking water, breathable oxygen, and rocket fuel, making a sustained human presence on the Moon far more feasible. In this sense, the South Pole Aitken Basin is not just a scientific gold mine, it is a strategic location for the future of humanity in space. Exploring this vast and rugged basin, however, presents formidable challenges. Its location on the far side means that any lander or rover would require a relay satellite for communication with Earth. Its rugged, cratered terrain would be difficult to navigate, and the permanently shadowed regions within it are some of the coldest places in the entire solar system, with temperatures plunging to hundreds of degrees below zero. Operating robotic or human systems in such an extreme environment would demand cutting-edge technology and innovative engineering. Yet despite these hurdles, the scientific and strategic allure of the South Pole Aitken Basin is irresistible. In January of 2019, China's Chang'e 4 mission achieved the historic first soft landing on the far side of the Moon, touching down in the von Karman crater, which lies within the basin. Its rover Yutu-2 has been exploring this ancient terrain, providing the first ground-level view of this remarkable geological feature. Though not a NASA mission, its success has proven that exploration of this extreme environment is possible and has highlighted the international fascination with this extraordinary lunar frontier. Looking to the future, NASA and other space agencies have their sights set on further exploration of the basin, with plans for both robotic and eventually human missions. Among the most exciting goals is a sample return mission, which would bring back the first actual rocks from the far side and specifically from this ancient mantle-exposing basin. Such samples would be a scientific treasure revealing unprecedented secrets about the Moon's origin, its deep interior, and the earliest days of our solar system. Every mission, every measurement, every carefully collected piece of data brings us one step closer to unraveling the ancient stories that are written in the rocks of this immense and shadowed basin, a place that continues to challenge our explorers while offering a scientific prize unlike any other. The face of the Moon is a tale of two worlds, a dramatic and enduring asymmetry that is etched into its very surface. This dichotomy is most apparent in the distribution of its craters. The Moon is a cosmic archive, its surface a preserved record of the billions of years of bombardment it has endured since its formation. Unlike the Earth, where wind, water, and tectonic activity constantly erase the scars of the past, the Moon is a quiet, airless world where impact craters can survive for eons. But these craters are not spread evenly across its surface. There is a stark and fundamental difference between the near side, the hemisphere that perennially faces Earth, and the far side, the hemisphere that remained hidden until the dawn of the space age. The careful exploration of the Moon by NASA and other space agencies has revealed the nature of this dramatic difference and has helped to explain the deep geological forces that have given our Moon its two distinct faces. Looking at the Moon from Earth, even with the naked eye, you can see two different types of terrain: the bright, rugged highlands, which are heavily pockmarked with craters, and the darker, smoother plains known as the Maria. These Maria, once mistaken for seas by early astronomers, are vast basins that were filled with basaltic lava billions of years ago. These lava flows resurfaced large areas of the near side, effectively paving over and obliterating many of the older impact craters. This has given the near side a more varied and, in many places, a geologically younger surface. The far side, however, tells a very different story. The first robotic probes, later confirmed by the direct observations of the Apollo astronauts and the detailed maps from modern orbiters, revealed a landscape that is almost entirely covered by the bright, heavily cratered highlands. The large, dark Maria are conspicuously rare. The scenery is dominated by craters of all sizes, from tiny pits to vast, multi-ringed basins. It is an ancient, battered, and almost uniformly rugged expanse, far more densely cratered than the near side. This striking contrast is one of the Moon's most fundamental and mysterious features, and NASA's missions have provided compelling explanations for this profound asymmetry. The key factor appears to be the thickness of the Moon's crust. Detailed measurements from missions like Lunar Prospector and the Gravity Recovery and Interior Laboratory, or GRAIL, have shown that the far side's crust is on average significantly thicker than the near side's. The far side's crust is about 60 kilometers or 37 miles thick, while the near side's averages only about 30 kilometers or 18.5 miles. This difference has had a profound effect on the Moon's geological evolution. This uneven crust likely formed very early in the Moon's history during the cooling of the primordial magma ocean. One leading theory suggests that the gravitational pull of the Earth may have played a role pulling the Moon's molten core slightly off-center and resulting in a thinner crust on the Earth-facing side. Whatever the exact cause, this initial asymmetry set the stage for the divergent evolution of the two hemispheres. The thickness of the crust directly affected the ability of volcanic activity to reshape the surface. On the near side, the relatively thin crust was more easily fractured by large impacts, providing conduits for molten lava from the Moon's interior to rise to the surface. These massive lava flows filled the great impact basins, forming the Dark Maria and covering up many of the older craters. On the far side, the thick crust acted as a formidable barrier. Even when enormous impact basins were formed, like the colossal South Pole Aitken Basin, magma from the interior could not easily break through to the surface. As a result, the far side's ancient craters remained largely untouched, preserved for billions of years. The far side, therefore, tells a story of ancient bombardment that is almost entirely undisturbed, while the near side shows a landscape that has been partially reshaped and rejuvenated by volcanic activity. Another crucial factor contributing to this volcanic asymmetry is the uneven distribution of heat-producing radioactive elements within the Moon. Data from Lunar Prospector's gamma-ray spectrometer revealed a surprising concentration of elements like potassium, uranium, and thorium on the near side of the Moon in a region known as the Procellarum creep terrain. These radioactive elements decay over time, releasing heat. Their higher concentration on the near side would have kept the mantle beneath it warmer and more molten for a longer period, fueling the widespread volcanic eruptions that created the Maria. The far side, with a lower concentration of these heat-producing elements, would have had a cooler interior that solidified more quickly, leading to far less volcanic activity. This uneven distribution of the Moon's internal heat engine played a critical role in shaping the very different geological histories of the two hemispheres. The way NASA unraveled this complex story involved a series of increasingly sophisticated missions. After the initial visual confirmation of the far side's rugged nature from Luna 3, NASA's Lunar Orbiter program in the mid-1960s provided the first systematic high-resolution photographic coverage, clearly showing the dominance of the highlands and the lack of Maria. Later missions used more advanced instruments to quantify these differences. The Clementine mission in 1994 carried a laser altimeter that meticulously mapped the Moon's topography, confirming the higher average elevation of the far side highlands. Lunar Prospector in 1998 was a key mission for mapping the Moon's gravity and its elemental composition. Its gravity maps revealed the existence of mascons, or mass concentrations, associated with the dense lava flows of the near-side Maria features that are largely absent on the far side. And its gamma-ray spectrometer provided the crucial data on the uneven distribution of radioactive elements, directly linking them to the asymmetry in volcanic activity. The Lunar Reconnaissance Orbiter, or LRO, launched in 2009, has provided the most detailed and comprehensive data yet. Its laser altimeter, LOLA, has created breathtakingly precise three-dimensional models of the lunar surface, allowing scientists to measure the depths and diameters of craters on both sides with unprecedented accuracy. And its powerful camera system has taken millions of high-resolution images, revealing the fine details of the cratered terrain. The implications of this cratering dichotomy are profound. The far side, with its thicker, cooler crust and its preserved record of ancient impacts, is a unique window into the early history of the solar system. It is the best place to study the late heavy bombardment, the period of intense impacts that all the inner planets experienced. By studying the size distribution and degradation of craters on the far side, scientists can refine their models of this chaotic era and better understand the population of asteroids and comets that shaped our planetary neighborhood. The method of crater counting is a fundamental tool for planetary scientists to determine the relative ages of different surfaces. A more heavily cratered surface is generally older. By comparing the densely cratered far side with the less cratered near side, Maria, And by calibrating this with the absolute ages determined from the Apollo rock samples, scientists have built a detailed timeline of lunar geological history. This lunar timeline then serves as a crucial benchmark for dating the surfaces of other bodies in the solar system, like Mercury and Mars, where we have not yet been able to collect and date rock samples. The Moon's cratered surface, and especially the pristine record preserved on the far side, is a key to unlocking the history of the entire inner solar system. Studying the Moon's two different faces also tells us a great deal about the history of our own planet. The Earth must have experienced the same intense bombardment as the Moon in its early history, but the evidence has been almost completely erased by billions of years of erosion, volcanism, and plate tectonics. The Moon in this sense acts as a silent witness, its battered face preserving the story of the cosmic violence that both it and the Earth endured in their youth. Looking ahead to future exploration, the far side's ancient, heavily cratered surface presents both unique challenges and unique scientific opportunities. Its rugged terrain makes landing and traversing difficult for robotic and human missions. But its pristine ancient nature makes it a prime target for sample return missions that could give us access to the oldest materials in the Earth-Moon system, providing definitive answers about the Moon's formation and the early history of the solar system. And its radio-quiet environment shielded from the Earth makes it the ideal location for the next generation of radio telescopes which could unlock the secrets of the cosmic dawn. The Moon's two very different worlds, the familiar near side and the hidden far side, continue to provide a rich and fascinating story of planetary evolution, a story that is being slowly and carefully pieced together by our ongoing exploration of our closest celestial neighbor. The surface of the Moon is a geological tapestry woven from two distinct threads, the dark, relatively smooth volcanic plains of the Maria and the bright, rugged, and ancient highlands. The highlands are the dominant terrain covering the majority of the Moon's surface and almost the entirety of the far side. These are not just ancient hills and valleys, they are immense geological time capsules, the preserved remnants of the Moon's very first crust. Their age, their composition, and the countless craters that scar their surface tell the story of the Moon's fiery birth, its initial separation into layers, and the violent cosmic environment of the early solar system. Over decades of exploration, NASA's robotic and human missions have painstakingly unlocked these stories, revealing clues not just about the Moon's origins, but about the formation of all the rocky worlds in our cosmic neighborhood. The lunar highlands are truly ancient, representing the oldest surviving crust of our celestial companion. Scientists estimate that they formed during the Moon's very first few 100 million years, between 4.5 and 4 billion years ago. This makes them significantly older than the dark Maria, which formed later from volcanic eruptions. The story of the highlands' birth is tied to a central theory of lunar formation known as the lunar magma ocean hypothesis. According to this idea, shortly after the Moon formed from the debris of a giant impact with the early Earth, it was a completely or largely molten world, a glowing global ocean of molten rock. As this enormous magma ocean began to cool over millions of years, a process of differentiation began. Heavier minerals like olivine and pyroxene sank toward the Moon's center, forming its mantle and core. Lighter minerals, especially a type of feldspar called plagioclase, floated to the top like cream rising in milk. This buoyant, low-density mineral gradually accumulated and solidified to form a thick global crust. This primordial crust, made primarily of a rock called anorthosite, which is composed almost entirely of plagioclase feldspar, became the lunar highlands. This process is what gave the Moon its layered structure, and in many places, especially on the far side, the highlands remain as a pristine, untouched remnant of this original surface. Perhaps the most striking feature of the highlands is their incredible density of impact craters. From vast, multi-ringed basins to tiny pits, the highlands are saturated with the scars of ancient collisions. This is dramatic evidence of the late heavy bombardment, a violent period in the early solar system, when the rate of asteroid and comet impacts was far higher than it is today. Because the highlands had already formed and have remained largely geologically inactive since they preserve the full unedited record of this ancient cosmic assault. The preservation of these craters, particularly on the far side, is directly linked to the thickness of the crust. Because the far side's crust is thicker and its interior is cooler, it experienced far less volcanic activity than the near side. On the near side, lava flows filled many of the ancient impact basins, creating the smooth Maria. But the far side's highlands were largely spared this resurfacing, and as a result, they have accumulated impact scars for billions of years, serving as a frozen snapshot of the Moon's chaotic youth. NASA's decades of lunar exploration have given us a detailed understanding of the highlands' composition. The first direct evidence came from the Apollo missions. Though the astronauts landed primarily in the smoother Maria, they deliberately collected rock samples that were representative of the highlands, including fragments that had been blasted out of the highlands by nearby impacts. These precious samples, brought back to Earth for detailed laboratory analysis, confirmed that the highlands are indeed made primarily of anorthosite, the light-colored low-density rock predicted by the magma ocean hypothesis. Beyond the Apollo samples, NASA's robotic orbiters have mapped the composition of the entire lunar surface, including the far side. The Clementine mission in 1994 used multispectral cameras to identify the unique spectral signature of anorthosite, confirming its widespread presence in the highlands. The Lunar Prospector mission in 1998 carried a gamma-ray spectrometer that measured the elemental composition of the surface. Its data showed that the highlands have lower concentrations of iron and titanium compared to the basaltic Maria, which is consistent with the composition of anorthosite. Together, these missions have painted a detailed and consistent picture of the highlands as the Moon's ancient primordial crust, a record of its fiery birth and turbulent early life. The Lunar Reconnaissance Orbiter, or LRO, has dramatically deepened our understanding of the highlands. Its laser altimeter, LOLA, has mapped their topography with stunning precision. Its diviner instrument has measured their thermal properties, helping to identify different mineral types. And its powerful camera system has captured millions of high-resolution images that reveal the texture of the highland soil, or regolith, in exquisite detail. These images show that the surface is not made of solid, unbroken bedrock, but is largely composed of breccias rocks that are formed from the angular fragments of older rocks that have been fused together by the intense heat and pressure of countless impacts. This tells a story of a surface that has been shattered, churned, and recompacted over billions of years, a continuous record of cosmic violence. The scientific importance of the lunar highlands cannot be overstated. They are a kind of Rosetta Stone for understanding both the Moon's formation and the early history of our solar system. Their anorthositic composition provides the strongest evidence for the lunar magma ocean hypothesis, helping us to refine our models of how the Moon and other rocky bodies differentiated into layers. They are also crucial for establishing a timeline of solar system events. Because they preserve the oldest and most continuous record of impacts, they allow us to calibrate the method of crater counting, which is our primary tool for dating the surfaces of other planets. In addition, the highlands offer a rare glimpse into the process of early planetary evolution. The Earth's original crust has been completely erased by billions of years of geological activity. The Moon's highlands, in contrast, have remained largely intact. They are a fossil record preserving what the surface of a rocky planet looked like in its infancy. Studying these ancient terrains allows us to learn how terrestrial planets formed their first crusts and how they were shaped by the massive impacts of the early solar system. While the highlands are not generally rich in resources like water ice, their ancient and unique composition may hold other valuable materials. And from an exploration standpoint, untouched regions of the far side highlands are highly attractive targets for future sample return missions. Bringing back pristine samples of the oldest lunar material could answer some of the most fundamental questions about the Moon's origin and the timing of key events in the early solar system. The study of the lunar highlands, led by decades of exploration by NASA and its international partners, has transformed our perception of the Moon. Once thought to be a simple static world, the Moon is now recognized as a dynamic body with a rich and complex history. The highlands are not just rugged ancient landscapes. They are natural laboratories offering priceless insights into the moon's fiery birth, its global differentiation, and the chaotic early days of the solar system. They continue to reveal secrets about the formation of rocky planets and the processes that shaped our cosmic neighborhood in its earliest and most violent chapters. For generations, the moon's cyclical journey through the night sky has been a familiar and comforting presence. Yet this very familiarity has given rise to a persistent and widespread misunderstanding, a piece of cosmic folklore that has woven itself into our language and culture, the idea of a dark side of the moon, a hemisphere that is perpetually cloaked in shadow, forever hidden from the light of the sun. This notion, though evocative, is entirely incorrect. It stems from a confusion between a side that is hidden from Earth and a side that is hidden from sunlight. Through decades of careful observation and exploration, particularly by NASA missions, this myth has been thoroughly and definitively debunked. The truth, supported by overwhelming scientific evidence, is that the entire moon, both the near side and the far side, experiences a regular and predictable cycle of day and night, just like our own planet. The root of this misunderstanding lies in the phenomenon of tidal locking. As we've seen, the moon's rotation is perfectly synchronized with its orbit, meaning that the same hemisphere always faces the Earth. The side that always faces us is the near side. The side that always faces away is the far side. Because we can never see the far side, it is often colloquially referred to as the dark side. But in this context, dark means hidden or unknown, not unlit. Sunlight, of course, comes from the sun, not from the Earth. The moon orbits the Earth, and this entire system orbits the sun. As the moon travels on its monthly journey, the sun illuminates different parts of its surface. Like the Earth, the moon has a terminator, the line that separates the sunlit day side from the shadowed night side. This line is constantly moving across the lunar surface as the moon rotates and orbits. A full lunar day, the time it takes for the sun to appear to move once across the lunar sky and return to the same position, is about 29.5 Earth days long. During this synodic month, every part of the moon's surface, including the far side, experiences roughly 14 Earth days of continuous brilliant sunlight, followed by roughly 14 Earth days of deep cold darkness. When the near side is experiencing its night, the far side is fully illuminated, enjoying its long lunar day. And when the near side is fully lit, as it is during a full moon, the far side is in the depths of its lunar night. Think about the phases of the moon as we see them from Earth. During a new moon, the moon appears dark to us because the side facing Earth is unlit by the sun. At that exact moment, the entire far side is bathed in sunlight. It is noon on the far side. During a full moon, the side facing us is completely illuminated. At that same moment, the entire far side is in complete darkness. It is midnight on the far side. As the moon moves through its phases, the line of sunlight sweeps steadily across both hemispheres. There is no side of the moon that is permanently dark. NASA played a key role in confirming this and dispelling the myth of the dark side. The very first mission to photograph the far side, the Soviet Luna 3 probe in 1959, had to time its flyby so that the far side was illuminated by the sun. Otherwise, its cameras would have seen nothing but blackness. Those first blurry images were the first proof that the far side receives sunlight. But it was NASA's Apollo program that provided the first direct human confirmation. As the crew of Apollo 8 orbited the moon in December of 1968, they became the first humans to see the far side up close. Their live television broadcasts, though grainy, clearly showed a sunlit landscape as they emerged from behind the moon. The famous Earthrise photograph taken by astronaut William Anders on that mission shows a beautiful crescent Earth rising above a rocky, sunlit lunar horizon. The lunar surface in the foreground of that iconic image is part of the far side clearly illuminated by the sun. The astronauts' own descriptions made it clear that the far side experiences periods of full daylight. Later, Apollo missions further solidified this understanding. Every mission to orbit the moon from Apollo 8 to Apollo 17 passed repeatedly over the far side, and the astronauts on board watched and photographed it under various lighting conditions. The thousands of photographs from these missions are an undeniable and comprehensive record showing the moving terminator and the full glare of the sun on the far side during its lunar day. Beyond the Apollo missions, NASA's robotic explorers have provided even more detailed and quantitative proof. The Lunar Orbiter program in the 1960s systematically photographed nearly the entire lunar surface, including the far side under different lighting conditions. More recently, the Lunar Reconnaissance Orbiter, or LRO, has been continuously mapping the Moon since 2009. Its powerful cameras have taken millions of high-resolution images of the far side, all of which are publicly available. These images clearly show the far side glowing under the sun's light during its daytime. LRO also carries other instruments that provide indirect evidence of the day-night cycle. Its Diviner instrument measures the temperature of the lunar surface. The data from Diviner reveal dramatic temperature swings on the far side. During the long lunar day, the surface temperature can soar to over 100 degrees Celsius or 212 degrees Fahrenheit. During the long lunar night, it plunges to as low as -173 degrees Celsius or -280 degrees Fahrenheit. These extreme temperature changes are a direct result of the surface being heated by the sun and then rapidly cooling in its absence. If the far side were always dark, its temperature would remain consistently, unimaginably cold. So, while the term dark side persists in our popular culture, it is a poetic misnomer. The more accurate scientific term is the far side. It is a land that is hidden from our view, but not from the light of the sun. The only places on the Moon that are truly in permanent darkness are the floors of some deep craters near the lunar poles. Due to the Moon's very slight axial tilt, the sun is always very low on the horizon at the poles, and it never reaches into the bottom of these deep shadowed regions. These permanently shadowed craters are rare and isolated pockets of eternal night, while the vast majority of the Moon's surface on both the near and the far sides enjoys its own long, slow cycle of day and night. For much of the 20th century, the scientific consensus was that the Moon was a completely dry, barren world. The rock samples brought back by the Apollo astronauts in the 1960s and 70s seemed to confirm this view. They were found to be almost completely devoid of water. This bone-dry model of the Moon had a profound influence on our plans for future exploration, suggesting that any long-term human presence would have to be supported by a continuous and expensive supply of water brought from Earth. But over the last few decades, this picture has been completely transformed. Thanks to a series of advanced robotic missions, many led by NASA, our understanding of water on the Moon has undergone a revolution. The Moon, it turns out, is not as dry as we once thought. It holds a valuable and surprising secret deposits of water ice hidden in the coldest and darkest corners of its polar regions. The search for this lunar water has become a central focus of modern planetary science, with profound implications for the future of human exploration. The first strong clues came from NASA's Clementine mission in 1994. The orbiting spacecraft carried a radar experiment that bounced radio signals off the Moon's surface. In some of the permanently shadowed craters near the Moon's south pole, the reflected signals showed an unusual signature, a pattern that was consistent with the presence of water ice. While not definitive proof, Clementine's data sparked renewed scientific interest and set the stage for future missions to investigate the lunar poles. A few years later, in 1998, NASA's Lunar Prospector mission provided much stronger evidence. It carried a neutron spectrometer, an instrument that could detect the presence of hydrogen. When cosmic rays strike the lunar surface, they create a spray of neutrons. If these neutrons encounter hydrogen atoms, they slow down in a predictable way. Lunar Prospector's instrument detected a significant concentration of slow neutrons coming from the permanently shadowed craters at both the north and south poles, indicating a high concentration of hydrogen. The most likely form for this hydrogen to take in these extremely cold regions was water ice. This mission moved the idea of lunar ice from speculation to strong probability. The reason water ice can survive on the Moon is due to the unique conditions at the poles. The moon's axis is tilted by only about 1.5 degrees relative to its orbit around the sun. This tiny tilt means that at the poles, the sun is always very low on the horizon. As a result, the floors of some deep craters are in a state of permanent shadow. They have not seen direct sunlight for billions of years. In these permanently shadowed regions, temperatures are unimaginably cold, plunging to as low as -240 degrees Celsius or -400 degrees Fahrenheit. At these cryogenic temperatures, water ice is incredibly stable. It can persist for billions of years, resisting the tendency to sublimate directly into gas and escape into space. These permanently shadowed regions act as cosmic cold traps, collecting and preserving any volatile materials, including water, that find their way there. This water is thought to have been delivered to the moon over billions of years by comets and asteroids, which often contain large amounts of ice. When these objects impact the moon, some of the water vapor created in the collision can migrate across the surface and become trapped in these polar cold spots. In addition, the solar wind, a constant stream of charged particles from the sun, implants hydrogen into the lunar soil. This hydrogen can combine with oxygen in the lunar minerals to form small amounts of water, some of which can also migrate to the cold traps. The definitive proof of water ice came in 2009 from a bold and innovative NASA mission called the Lunar Crater Observation and Sensing Satellite, or LSROS. The mission had two parts, a used Centaur rocket stage and a shepherding spacecraft. In October of 2009, the Centaur rocket stage was intentionally crashed into Cabeus crater, a large permanently shadowed crater near the moon's south pole. The impact created a plume of debris that was blasted up into the sunlight above the crater rim. The shepherding spacecraft then flew through this plume, analyzing its composition with a suite of instruments before it too impacted the surface. The data from LSROS was unambiguous. Its spectrometers detected the clear and unmistakable spectral signatures of both water vapor and water ice in the plume. It was a groundbreaking discovery, the first direct detection of water on the moon. It transformed our understanding from strong inference to established fact. At the same time, NASA's Lunar Reconnaissance Orbiter, or LRO, which is still orbiting the moon today, has been providing a wealth of detailed data about these polar ice deposits. LRO's laser altimeter has created precise three-dimensional maps of the lunar poles, identifying and characterizing thousands of permanently shadowed regions. Its diviner instrument has measured their temperatures, confirming that they are indeed cold enough to trap ice. While LRO cannot see the ice directly in the darkness, its data has been crucial for understanding the environment where the ice exists and for identifying the most promising locations for future exploration. The evidence suggests that the ice is not in the form of thick, pure sheets like glaciers on Earth. Instead, it is likely mixed in with the lunar soil, or regolith perhaps, as ice crystals or frost, with concentrations varying from a few percent up to perhaps 20% by weight in some areas. The total amount of water ice is still being estimated, but current models suggest that there could be hundreds of millions, perhaps even billions of tons distributed across both poles. The confirmed presence of this water ice has profound implications for the future of space exploration. Water is an incredibly valuable resource in space. It is essential for human life, for drinking hygiene and growing food. Having a local source of water on the moon would dramatically reduce the cost and complexity of long-term human missions and lunar bases, as it would not need to be launched from Earth. But the value of lunar water extends far beyond life support. Water can be split into its constituent elements, hydrogen and oxygen, through electrolysis. Hydrogen and oxygen are the two primary components of the most powerful and efficient chemical rocket fuel. If water ice can be mined and processed on the moon, it could be used to create a refueling station in space. Rockets traveling from Earth could top up their tanks at a lunar propellant depot before heading on to more distant destinations like Mars. This concept of in situ resource utilization, or ISRU, is central to NASA's long-term vision for a sustainable human presence in space, and lunar water ice is its most critical target. NASA's Artemis program, which aims to return humans to the moon, is specifically targeting the South Pole because of the presence of this ice. Future robotic landers and rovers are being designed to explore these extreme cold traps, to map the extent and purity of the ice deposits, and to test the technologies that will be needed to extract and process this precious resource. The ultimate goal is to build a permanent, sustainable human presence on the moon, and access to water ice is considered the key to achieving this vision. The story of the search for water on the moon is a powerful example of how our scientific understanding is constantly evolving. For a long time, the moon was seen as a dry, dead, and desolate world. But through persistent and creative exploration, it has slowly revealed its surprising secret. It is not just a barren rock, but a world that holds a resource that could be the key to humanity's future in space. The once overlooked, permanently shadowed regions, thought to be just cold and dark, are now seen in a new light. They may be the most valuable places on the moon, the stepping stones for humanity's next giant leap into the cosmos. The moon's gravitational embrace is not a uniform, gentle pull. It is a complex and lumpy field of force, a landscape of subtle peaks and valleys that reflects the uneven distribution of mass deep within its interior. These tiny variations in gravity, known as gravity anomalies, are invisible to the eye, but can be felt by any spacecraft that ventures into lunar orbit. Over the decades, NASA's robotic probes have been crucial in mapping these anomalies, particularly on the far side, offering a remarkable way to peer beneath the moon's surface and to understand its hidden internal structure and its long, complex geological history. The first hints of these strange gravitational patterns were discovered almost by accident in the 1960s during the earliest lunar orbital missions. As NASA's lunar orbiter probes and later the Apollo command modules circled the moon, mission controllers noticed that the spacecraft were not following their predicted paths with perfect precision. They would subtly speed up or slow down, causing their orbits to shift in small but measurable ways. These deviations were not random. They occurred repeatedly over specific areas of the moon's surface, posing a new and unexpected challenge for navigation. Scientists soon realized that these orbital quirks were not due to errors in their calculations, but to real localized differences in the moon's gravitational pull. The areas of unexpectedly strong attraction were given the nickname mascons, short for mass concentrations. The first mascons were discovered to be associated with the large circular mare basins on the near side of the moon. These basins, like Mare Imbrium and Mare Serenitatis, are vast, low-lying plains that were filled with dense volcanic lava billions of years ago. The discovery that these basins contained hidden concentrations of mass beneath them was a surprising puzzle. To map these gravity anomalies with greater accuracy, NASA developed increasingly sophisticated tracking techniques. By carefully monitoring the radio signals sent from a spacecraft back to Earth, scientists could detect tiny changes in the signal's frequency caused by the Doppler effect. These frequency shifts revealed subtle changes in the spacecraft's velocity. A slight increase in speed meant the spacecraft was being pulled by a stronger gravitational field, while a decrease indicated a weaker field. This method provided the first rough maps of the moon's gravitational landscape. Over the following decades, dedicated gravity mapping missions dramatically improved our understanding. The greatest leap came with NASA's Gravity Recovery and Interior Laboratory, or GRAIL mission. Launched in 2011, GRAIL consisted of two identical spacecraft flying in close formation around the moon. The concept was beautifully simple. As the twin spacecraft passed over an area with stronger gravity, the leading craft would speed up slightly, increasing the distance between the two. As they passed over an area with weaker gravity, the opposite would happen. By measuring these minuscule changes in their relative distance with incredible micrometer-level precision, GRAIL was able to create the most detailed and accurate global gravity map of the moon ever produced. This map offered unprecedented insight into the far side, revealing features and structures that had been invisible before, and deepening our understanding of the Moon's hidden interior. One of the most remarkable revelations from Grail and other missions concerns the nature of the near-side mascons. Scientists now understand that these strong gravity highs are caused by a combination of the dense basaltic lava that fills the mare basins and a slight uplifting of the denser mantle material from beneath the thinned crust. The fact that these large mascons have persisted for billions of years tells a fascinating story about the Moon's internal rigidity. On a more geologically active body like the Earth, such a mass imbalance would be smoothed out over millions of years through a process called isostatic adjustment. But the Moon's outer shell, its lithosphere, cooled and hardened relatively quickly after its formation, freezing these mascons in place. They are gravitational fossils, preserving a record of the Moon's early, more dynamic history. When we turn our gaze to the far side, a very different picture emerges. The far side lacks the dramatic positive mascons found on the near side. This makes sense as the far side is largely missing the huge lava-filled basins that create them. Even the colossal South Pole Aitken Basin, the largest impact structure on the Moon, does not display a strong positive mascon. Its gravity signature is more complex and subtle, reinforcing the idea that the far side's thicker crust and different thermal history prevented the large-scale volcanic activity that defined the near side. Beyond these large-scale features, Grail's incredibly detailed maps revealed countless smaller anomalies scattered across the entire Moon. These often correspond to individual craters, buried volcanic structures, or hidden tectonic features like rifts and fractures. In essence, Grail allowed scientists to create a kind of X-ray of the Moon, revealing its inner architecture in 3 dimensions. The broader implications of these findings are profound. The precise gravity measurements, when combined with the topographic data from missions like LRO, have allowed scientists to map the thickness of the Moon's crust in exquisite detail. These models confirm that the far side has a thicker crust, while the near side beneath the Maria has a thinned crust. This gravity data also helps to reveal the structure of the mantle and even the size and state of the Moon's small core, providing a full 3-dimensional picture of its internal layering. The contrast between the near and far sides highlights a deep asymmetry that extends far below the surface, a reflection of the uneven processes that shaped the Moon in its earliest days. Grail's meticulous gravity mapping has unveiled a Moon that is both rigid and complex, a world that has preserved the secrets of its ancient violent history in the subtle invisible landscape of its own gravitational field. The Moon we see today is a magnetically quiet world. Unlike the Earth, which is wrapped in a powerful global magnetic field generated by a dynamo in its molten iron core, the Moon has no such protective shield. For many years, scientists assumed that the Moon's small, cool interior had never been capable of generating a magnetic field. But a series of surprising discoveries from NASA missions, especially those that studied the far side, have revealed a hidden magnetic past. Trapped within the Moon's ancient crustal rocks are faint localized magnetic fields, fossilized remnants of a time long ago when the Moon may have had an active Earth-like core and a strong global magnetic field. The first direct evidence of lunar magnetism came from the Apollo missions. Astronauts placed magnetometers on the lunar surface, which detected weak but measurable magnetic fields in the surrounding rocks. At the same time, orbiting instruments on the Apollo command modules also detected these localized magnetic anomalies from above. This was a surprising discovery, as a small geologically dead body like the Moon was not expected to have any magnetic field at all. The fields were not active, but remnant, meaning the rocks had acquired a magnetic signature at some point in their past and had held on to it for billions of years. The full extent and pattern of these crustal magnetic anomalies became clearer with later robotic missions. NASA's Lunar Prospector, launched in 1998, carried a magnetometer that created the first global maps of these weak magnetic fields. Its data revealed that these anomalies are scattered across the entire lunar surface, but they are surprisingly stronger and more common on the far side. This uneven distribution became a major scientific puzzle. In particular, some of the strongest magnetic anomalies on the far side were found to be located directly opposite some of the largest and youngest impact basins on the near side. The very existence of these strong remnant magnetic fields suggests that the rocks acquired their magnetism at a time when the Moon did have a global magnetic field generated by an internal dynamo. The strength of some of these ancient fields is too great to be explained by other mechanisms like temporary fields created by impacts. This implies that billions of years ago the Moon's small core was hotter and more molten than it is today, capable of generating a powerful magnetic field through the convective motion of its liquid iron. This discovery has revolutionized our understanding of the Moon's early evolution, revealing that it was not always a cold, inactive body, but may have once had a vibrant, dynamic interior. The timing of this ancient lunar dynamo can be inferred from the age of the magnetized rocks. The strongest magnetic anomalies are found in crustal rocks that formed between about 4.2 and 3.2 billion years ago. The lack of strong magnetism in younger rocks suggests that the lunar dynamo, after operating for perhaps a billion years, eventually weakened and shut down as the Moon's small core cooled and solidified. This left the Moon without a protective magnetic shield, exposing its surface to the harsh solar wind and cosmic radiation, which may have helped to strip away any early tenuous atmosphere it might have had. The concentration of stronger magnetic anomalies on the far side, especially those directly opposite large impact basins on the near side, provides a powerful clue about their formation. This is explained by the antipodal focusing hypothesis. According to this idea, the enormous impacts that created the great near-side basins like Mare Imbrium sent powerful seismic waves ringing through the Moon's interior. When these waves converged and focused on the opposite side of the Moon, the antipode they could have intensely shocked and heated the crustal rocks there. As these shocked rocks cooled in the presence of the Moon's active global magnetic field, they would have acquired and preserved a strong remnant magnetization. Since the antipodes of many of the largest near-side basins are located on the far side, this explains why magnetic anomalies are stronger and more common there. Adding to the fascination of lunar magnetism are the strange and beautiful features known as lunar swirls. These are unusual, bright, swirling patterns on the lunar surface that often have a delicate, almost painted appearance. They do not correspond to any topographic features like craters or hills, which makes them unique. Many of these swirls, including the most famous one, Reiner Gamma on the near side, are found to be located directly on top of strong, localized magnetic anomalies. The leading theory for their formation is that these small, localized magnetic fields act as miniature shields deflecting the charged particles of the solar wind. The solar wind normally darkens and weathers the lunar surface over time. By protecting the surface from this space, weathering the magnetic fields have kept the underlying soil brighter and less altered, creating the swirling patterns we see today. While Reiner Gamma is on the near side, similar though often smaller swirls are also found on the far side, always associated with magnetic anomalies. They are a beautiful and visible manifestation of the Moon's hidden magnetic past. The discovery of the Moon's ancient dynamo changes our understanding of how planetary magnetic fields work. It shows that even small celestial bodies can generate a strong global field for a significant period in their early history. This, in turn, provides crucial insights into the Moon's long-lost thermal past, suggesting a hotter, more dynamic interior than previously thought. And the uneven distribution of these magnetic fossils across the two hemispheres reinforces the profound and fundamental asymmetry that defines our Moon, a difference that runs deep into its internal structure and is written in the invisible language of its ancient frozen magnetic fields. The surface of the Moon at first glance may seem a uniform landscape of gray dust and rock. Yet a closer look through the eyes of sophisticated orbiting instruments reveals a rich and complex tapestry of different minerals and rock types, each telling a piece of the Moon's long and dramatic story. Understanding this lunar geology is essential for unraveling the secrets of the moon's birth, its evolution, and the hidden structure that lies beneath its surface. Most of the moon's rocks are igneous, meaning they were formed from the cooling and hardening of molten rock. But its surface also contains vast quantities of breccias rocks, made from the fragments of older rocks that have been smashed and welded together by the intense heat and pressure of meteorite impacts. NASA's lunar missions from the Apollo astronauts who brought back precious rock samples to the robotic orbiters that have mapped the entire surface have allowed scientists to identify these different rock types and to compare the familiar near side with the mysterious far side, revealing a story of profound geological asymmetry. The most common and widespread mineral on the moon is plagioclase feldspar. This light-colored, low-density mineral is the primary component of a rock called anorthosite, which dominates the moon's bright, rugged highlands. Scientists believe that this anorthosite formed very early in the moon's history, crystallizing from a global ocean of molten rock and floating to the surface to form the moon's primordial crust. The widespread presence of anorthosite, especially on the far side, is the strongest evidence we have for this lunar magma ocean hypothesis, a theory that explains the moon's initial separation into a dense core, a mantle, and a lighter crust. In stark contrast, the moon's dark, smooth plains, the Maria, are made mostly of a very different rock basalt. Lunar basalts are dark, fine-grained rocks that are rich in iron and magnesium-bearing minerals like pyroxene and olivine. They were formed from volcanic activity when molten lava from the moon's interior flooded the great impact basins and solidified. The presence of pyroxene and olivine is particularly interesting, as these are minerals that are thought to make up the bulk of the moon's mantle, confirming that the lavas of the Maria originated from the partial melting of material deep inside the moon. Another special and scientifically important rock type is known as creep, an acronym for rocks that are rich in potassium, rare earth elements, and phosphorus. These are incompatible elements that do not easily fit into the crystal structure of common rock-forming minerals. As the lunar magma ocean solidified, these elements became concentrated in the last remaining pockets of molten rock. The uneven distribution of these creep-rich rocks, which are found almost exclusively on the near side, provides crucial clues about the moon's uneven volcanic activity and its long-term thermal evolution. The most direct way scientists have studied the moon's rocks is by analyzing the 382 kilograms, or 842 pounds of lunar material brought back by the Apollo astronauts. These samples, collected from 6 different landing sites on the near side, confirmed that anorthosite dominates the highlands and basalt forms the Maria. But to study the rest of the moon, and especially the far side, which has never been visited by humans, scientists rely on remote sensing instruments aboard orbiting spacecraft. One of the most powerful tools for this kind of remote geology has been the gamma-ray spectrometer, carried on missions like NASA's Lunar Prospector. This instrument can detect the unique gamma-ray signatures emitted by different chemical elements on the lunar surface, allowing scientists to create global maps of their abundance. On the far side, these maps show much lower concentrations of iron, titanium, and thorium compared to the near-side Maria. This strongly supports the idea that the far side highlands are made mostly of anorthosite, which is poor in these elements. The lower thorium levels also confirmed that the heat-producing creep materials are concentrated on the near side. Earlier, NASA's Clementine mission in 1994 carried a multispectral imager that photographed the moon in different wavelengths of light. Different minerals reflect light differently, creating unique spectral signatures. Clementine's data helped to create the first global mineralogical map of the moon, confirming the dominance of anorthositic rocks in the highlands of both the near and far sides. It also revealed intriguing signs of the mantle minerals pyroxene and olivine, especially in the vast South Pole Aitken Basin, indicating that this massive impact had excavated material from deep within the moon. More recently, NASA's Lunar Reconnaissance Orbiter has provided the most detailed compositional maps yet. Its Diviner instrument measures the thermal radiation from the surface. Different minerals emit heat in distinct ways, creating a kind of thermal fingerprint. Diviner has used these fingerprints to create detailed global maps of the Moon's primary rock types, confirming the anorthositic nature of the highlands and the basaltic composition of the Maria with unprecedented precision. Some of the most exciting discoveries have come from the far side, particularly from the South Pole Aitken Basin. Data from these orbiting instruments strongly suggest that this giant basin exposes rocks from deep within the lunar crust and possibly even the upper mantle. Scientists have detected significant concentrations of olivine and pyroxene on the basin floor. This is incredibly important as it shows that the SPA impact was so powerful that it effectively drilled a hole through the crust, giving us a rare glimpse into the Moon's inner layers without having to physically go there. The detailed maps created by these orbiting instruments have provided clear and undeniable proof that the Moon is a geologically asymmetrical world. The crust on the far side is fundamentally different from the crust on the near side. This strong contrast between a far side dominated by a thick, ancient, anorthositic crust and a near side with a thinner crust and large basalt-filled plains is a direct consequence of the processes that occurred during the Moon's formation and its early evolution. The far side highlands, with their ancient and largely untouched crust, act as a time capsule preserving a record of the earliest moments of the Moon's history, including the formation of its first crust and the violent era of heavy bombardment that followed. Every new piece of data from NASA's orbiters adds another piece to this grand puzzle, revealing a world with two very different faces, each recording a different chapter of its long and complex geological story. When you gaze at the Moon from Earth, its face is a familiar canvas of light and shadow, a patchwork of bright cratered highlands and dark smooth plains. These dark plains, the Maria, are the most prominent features of the near side, covering roughly 30% of its surface and giving it the iconic man in the moon appearance. They are vast, solidified floods of basaltic lava, the remnants of an ancient era of intense volcanic activity. But when we turn our attention to the far side, the hidden hemisphere, a profound geological mystery emerges. The Maria are almost entirely absent. The far side is a world of bright, rugged highlands with volcanic plains covering barely 1% of its surface. This dramatic imbalance, this volcanic dichotomy between the two hemispheres, has puzzled scientists for decades. Through careful and persistent exploration, NASA missions have provided the most compelling clues to explain why these dark volcanic seas are so rare on the far side. To understand this mystery, it helps to remember how the lunar Maria formed. They are not classic cone-shaped volcanoes like those on Earth. They are enormous flood basalt provinces. The story begins with giant asteroid impacts that carved out immense basins. Over the millions of years that followed, molten lava from the Moon's interior rose through fractures in the thinned crust and flooded these basins, creating the smooth, dark plains we see today. Most of this volcanic activity occurred between 3.8 and 3.2 billion years ago. The stark difference between the near and far sides is immediately apparent on any global lunar map. The near side is patterned with these large, dark Maria. The far side is an almost unbroken expanse of bright, ancient highlands. This sharp contrast is one of the Moon's most striking features, and it holds the key to understanding its internal structure and evolution. The most widely accepted explanation, supported by a wealth of data from NASA missions, revolves around a simple but powerful idea: a difference in crustal thickness. Data from missions like Grail have confirmed with remarkable precision that the far side's crust is on average about 60 kilometers thick, while the near side's crust is much thinner, averaging only about 30 kilometers. This variation had a huge effect on the Moon's volcanic activity. Magma, being less dense than the surrounding solid rock, naturally tries to rise to the surface, but a thick crust makes this journey far more difficult. On the near side, the thinner crust provided an easier path for lava to reach the surface and fill the great impact basins. On the far side, the thick crust acted as a formidable barrier, preventing all but the most minor eruptions. As a result, the far side remains dominated by its rugged ancient highlands, largely untouched by the volcanic resurfacing that gave the near side its characteristic dark seas. A second complementary explanation involves the uneven distribution of heat-producing radioactive elements. As we've seen, data from NASA's Lunar Prospector mission revealed that elements like potassium, uranium, and thorium are far more abundant on the near side in the Procellarum creep terrain. This concentration of radioactive elements would have kept the near side's mantle hotter for longer, producing more magma and fueling the extensive volcanic activity. The far side, with less of this internal heat source, had a cooler interior that produced far less magma. In other words, the Moon's internal engine was lopsided, with the near side being a volcanic hotspot, while the far side remained comparatively cold and quiet. It is important to note that the far side does have massive impact basins, including the South Pole Aitken Basin, the largest on the Moon. But despite the presence of these vast depressions, the combination of a thicker crust and a cooler interior prevented them from being flooded with lava. This shows that a giant impact alone was not enough to create a mare. The geological conditions beneath the surface were the deciding factor. NASA's multi-instrument approach has been key to unraveling this volcanic mystery. Visual mapping from missions like Lunar Orbiter and LRO has clearly shown the global distribution of Maria and confirmed their scarcity on the far side. Topographic measurements from missions like Clementine and LRO's laser altimeter have allowed for precise estimates of crustal thickness across the entire Moon, directly supporting the central theory. Gravity mapping, especially by Grail, has revealed the mascons associated with the dense near-side Maria features that are absent on the far side. And compositional mapping from instruments on Lunar Prospector and LRO has confirmed the basaltic nature of the Maria, the anorthositic nature of the highlands, and the near-side concentration of the heat-producing creep elements. The scarcity of Maria on the far side is not the result of a single factor, but a combination of conditions: a thicker crust, a cooler interior, and a different history of large impacts. Together, these elements paint a picture of a Moon whose volcanic history was remarkably one-sided, with the near side being a world of fiery floods, while the far side remained largely silent and frozen in its ancient cratered state. This volcanic imbalance is one of the clearest signs that the Moon did not evolve as a uniform body. It offers vital clues about the Moon's thermal history and the processes that shaped its crust in the earliest days of the solar system. The far side, precisely because it was spared the enormous lava floods that transformed the near side, serves as a relatively untouched record of the Moon's earliest history. A pristine window into a time when our entire solar system was a far more violent and chaotic place. The surface of the Moon is a profoundly hostile environment, a place where the delicate chemistry of life would be instantly extinguished. One of the primary reasons for this hostility is the constant, intense, and unfiltered bombardment of space radiation. Unlike the Earth, which is cocooned in the protective layers of a thick atmosphere and a powerful magnetic field, the Moon has neither of these vital shields. As a result, its surface is directly exposed to the full, unmitigated fury of cosmic and solar radiation. This exposure poses a serious health risk for future human explorers and creates significant challenges for the long-term operation of any equipment we place there. NASA has devoted considerable resources to studying this radiation environment, particularly through missions like the Lunar Reconnaissance Orbiter and the direct experiences of the Apollo astronauts. Understanding these radiation levels, especially on the far side, is absolutely essential for planning any sustainable human presence beyond the relative safety of low Earth orbit. Space radiation comes from two main sources: galactic cosmic rays, or GCRs, and solar particle events, or SPEs. Galactic cosmic rays are incredibly high-energy particles, mostly the nuclei of atoms, that have been stripped of their electrons and accelerated to near the speed of light by violent events like supernova explosions in distant galaxies. GCRs are ever-present, forming a continuous low-level background of radiation that permeates the entire solar system. Because of their extremely high energy, they are highly penetrating, able to pass through spacecraft walls and astronaut suits, making them very difficult to shield against. Long-term exposure to GCRs is a major concern for the health of astronauts on long-duration missions. Solar particle events. In contrast are sudden, intense, and unpredictable bursts of high-energy particles, mostly protons, that are ejected from the Sun during powerful solar flares or coronal mass ejections. While the background radiation from GCRs is a chronic long-term threat, a strong SPE can deliver a dangerous, even lethal dose of radiation in a very short period. These events are the acute, immediate threat that astronauts on the lunar surface would have to be prepared for. The Earth, in stark contrast, enjoys powerful natural protection. Our planet's global magnetic field deflects most of these charged particles, and our thick atmosphere absorbs most of what gets through. The Moon has no such defenses. Its entire surface, both near and far side, is completely exposed. NASA first began to gather direct data on this radiation environment during the Apollo missions. Astronauts carried personal dosimeters that recorded their total radiation exposure, and these measurements confirmed that the levels on the Moon were far higher than in Earth orbit. While the short duration of the Apollo missions limited the astronauts' total exposure, the risk of a sudden solar particle event was a constant concern. The most thorough and continuous measurements of lunar radiation have come from NASA's Lunar Reconnaissance Orbiter, or LRO. It carries a specialized instrument called the Cosmic Ray Telescope for the effects of radiation, or crater. This instrument is designed to measure the full spectrum of lunar radiation and to study how different shielding materials can reduce its effects. Its detectors are made from a tissue-equivalent plastic that mimics human tissue, allowing scientists to directly estimate the biological dose that an astronaut would receive. Crater's data has confirmed that the radiation environment on the lunar surface is harsh, with dose rates roughly 2 to 3 times higher than on the International Space Station, which is still partially protected by the Earth's magnetic field. While the Moon itself provides some shielding from radiation, coming from below an astronaut on the surface is exposed to the full sky. In recent years, scientists have been able to obtain the first direct long-term measurements of radiation on the far side thanks to an instrument on China's Chang'e 4 lander. These measurements have largely confirmed what was inferred from orbit by LRO. The radiation environment on the far side is broadly similar to that on the near side. This is what we would expect, as the Moon lacks the global shields that would create any significant difference between the hemispheres. Understanding this radiation environment is critical for planning future human missions. The long-term health risks from exposure to GCRs include an increased lifetime risk of cancer damage to the central nervous system and degenerative tissue diseases. The acute risk from a solar particle event is radiation sickness, which can be incapacitating or fatal. To mitigate these risks, any long-term human habitat on the Moon will require substantial shielding. One of the most effective and readily available shielding materials is the lunar regolith itself. Future lunar bases may be built underground or covered with several meters of soil, which would provide significant protection from both GCRs and SPEs. In addition to physical shielding, robust early warning systems will be vital. A network of satellites monitoring the Sun could alert a lunar crew to an incoming solar particle event, giving them time to take shelter in a heavily shielded storm cellar within their habitat. While the Moon's lack of a global magnetic field makes the radiation environment broadly similar across its surface, there are subtle differences. The Earth's magnetotail, a long extension of our planet's magnetic field, occasionally sweeps across the near side of the Moon, offering a slight and temporary reduction in solar particle flux. The far side lies almost entirely outside this minor shielding effect, experiencing a more consistent and direct exposure. More importantly, if a major SPE occurs while astronauts are on the far side and therefore out of direct communication with Earth, receiving a real-time warning becomes impossible. This highlights the need for autonomous on-site radiation monitoring and emergency protocols that can be executed without immediate guidance from mission control. Thanks to decades of data from NASA missions and their international partners, we now have a detailed picture of the Moon's harsh radiation environment, a critical piece of knowledge that will allow us to design the systems and strategies needed to ensure the health and safety of the next generation of lunar explorers. Just as earthquakes on Earth send seismic waves rippling through our planet, revealing the structure of its crust mantle and core, the Moon experiences its own subtle tremors called moonquakes. Studying these faint vibrations is the science of lunar seismology, and it provides a unique and powerful way to probe the Moon's hidden interior. Although the Apollo astronauts only placed seismometers on the near side of the Moon, the long reach of these seismic waves has allowed scientists to infer the structure of the entire Moon, including the far side, giving us our first deep understanding of its internal layering. The Apollo Lunar Seismic Network was a monumental scientific achievement. Beginning with Apollo 11 and with more advanced instruments deployed on Apollos 12, 14, 15, and 16. NASA created a network of 4 long-lasting seismic stations on the near side. These incredibly sensitive instruments listened continuously for the faintest vibrations on the lunar surface. Powered by radioisotope generators, they operated for more than 8 years, from 1969 to 1977, recording thousands of moonquakes and meteoroid impacts and transmitting their data back to Earth. Through these observations, scientists identified several different types of moonquakes. The most common are deep moonquakes, which originate hundreds of kilometers below the surface, deep within the Moon's mantle. These tremors are strongly linked to the tidal forces exerted by the Earth's gravity, occurring in a predictable monthly cycle as the Moon is stretched and squeezed in its orbit. Another type, shallow moonquakes, is much rarer but often stronger. They originate in the Moon's crust and are thought to be caused by stresses from the slow cooling and contraction of the Moon. In addition to these natural quakes, the Apollo network also recorded the impacts of meteoroids and, in a series of planned experiments, the intentional crashes of spent rocket stages and lunar modules onto the Moon's surface. These controlled impacts acted like precise seismic hammers, sending waves of unknown energy through the Moon that scientists could study to map its interior. The remarkable ability of this near-side network to listen to and interpret tremors originating from the far side was a stunning demonstration of the power of seismology. When a moonquake or a large impact occurred on the far side, it sent out seismic waves that traveled through the Moon's interior, eventually reaching the Apollo seismometers. There are 2 main types of seismic waves: P waves, or primary waves, which are compressional waves that can travel through both solids and liquids, and S waves, or secondary waves, which are shear waves that can only travel through solid material. By carefully measuring the arrival times of these waves at the different stations, scientists could pinpoint the location and depth of the seismic event. More importantly, the way these waves traveled through the Moon revealed critical clues about the density and rigidity of the materials they passed through. One of the most exciting breakthroughs was the discovery of a shadow zone for S waves. When a far-side moonquake occurred, the S waves traveling through the very center of the Moon were found to be missing or severely weakened when they reached the near-side seismometers. This was the smoking gun, the definitive evidence that the Moon has a small, partially molten core. Because S waves cannot travel through liquid, their absence proved that the very heart of the Moon is not entirely solid. This discovery was profound, overturning the long-held idea that the Moon's interior was completely cold and inert. Analysis of the seismic data has allowed scientists to estimate that this core is relatively small, making up only about 20% of the Moon's radius, and that it consists of a solid inner core surrounded by a fluid outer core. The seismic waves from far-side events also offered a window into the structure of the Moon's mantle and crust. The way the waves scattered and weakened revealed that the upper crust is highly fractured, a testament to billions of years of meteorite impacts. And though no seismometers were placed on the far side, the way the waves traveled through its crust and mantle provided indirect but valuable information, hinting at differences in structure that align with the gravity and topographic data. The Apollo seismic experiment, even with its instruments confined to one hemisphere, conclusively confirmed that the Moon has a layered interior, a crust, a mantle, and a small, partially molten core. It reshaped our models of the Moon's thermal evolution, revealing that it has retained more internal heat for longer than previously believed. And it demonstrated that the Moon is a tectonically quiet body, lacking the active plate tectonics that define our Earth. The Apollo seismometers, long since silenced, provided an invaluable legacy of data, a set of echoes from the Moon's deep interior that continue to guide our understanding of the hidden workings of our nearest celestial neighbor. You are aboard a spacecraft, floating in the silent, inky abyss of interstellar space. The stars outside your window are ancient, their light having stretched across millions of years to reach your eyes. Every movement, every signal sent from your ship takes time to travel minutes, hours, even years to cross the cosmic void. But then, something impossible happens. A message appears on your screen, not carried by radio waves, not transmitted through light, but teleported. Its information woven into the very fabric of quantum reality. It did not travel the distance between its origin and your ship. It simply appeared. This is not a scene from science fiction. It is the strange and beautiful reality of quantum teleportation, a process where information, not matter, is transferred instantaneously, breaking the traditional rules of space and time. Unlike the teleporters of futuristic movies, quantum teleportation does not transport objects or people, but rather the very essence of their quantum state, the fundamental informational blueprint that defines them. But how is this possible? How can something leap across space without physically moving? To answer this, we must journey into the depths of quantum mechanics, into a world where particles can exist in multiple states at once, where entanglement links objects across vast cosmic distances, and where reality itself appears to be nothing more than a fragile, shimmering web of probabilities. This is the story of quantum teleportation, a phenomenon that challenges the very nature of existence, a discovery that could one day revolutionize communication, computing, and perhaps even our understanding of the universe itself. But before we can unlock the secrets of teleportation, we must first understand the bizarre, counterintuitive, and wonderfully mysterious quantum world that makes it all possible. There was a time, not so long ago, when physics was simple. The world was a clockwork universe, a grand deterministic machine where objects had precise locations, forces acted predictably, and the future was, in principle, calculable from the present. But at the dawn of the 20th century, this elegant, common-sense picture began to crumble. The quantum revolution arrived. A theory so strange, so counterintuitive, so profoundly weird, that even its own architects, like Albert Einstein, struggled to accept its full implications. At the heart of this revolution lies a disturbing and beautiful truth at the smallest scales. The universe does not behave in any definite way until we observe it. To understand why this is so profound, picture a simple marble rolling across a smooth table. In the classical world of our everyday experience, if you knew its exact position and its exact velocity, you could predict its entire future trajectory with perfect certainty. But in the quantum world, this certainty dissolves. The quantum marble, an electron, for example, does not have a single, definite position. It exists as a wave of probability, a diffuse cloud of potential locations, a superposition of all the places it could possibly be. It is not here or there. It is, in a very real sense, both here and there, and everywhere else in between, all at the same time. It is only when an observer looks, when a measurement is made, that this shimmering cloud of possibilities collapses, and the electron chooses a single, definite location. This is not just a mathematical trick or a philosophical abstraction. It is an experimental fact, one that has been confirmed time and time again. The famous double-slit experiment demonstrates this with an almost mystical clarity. When a beam of electrons is fired at a barrier with two narrow slits, and we do not try to determine which slit each electron passes through, an interference pattern appears on a detector screen behind the barrier. This pattern of alternating bright and dark bands is the classic signature of waves interfering with each other, like the ripples from two stones dropped in a pond. This happens even if the electrons are fired one at a time. Each individual electron seems to pass through both slits simultaneously, as a wave, and then interfere with itself. But the moment we place a detector at one of the slits to watch which path the electron takes, the wave-like behavior vanishes. The interference pattern disappears, and we see two simple bands on the screen, corresponding to the two slits. The electron now behaves like a well-behaved particle, choosing one path or the other. The very act of measurement, of gaining information, has changed the nature of reality itself. But if the principle of superposition is strange, the phenomenon of quantum entanglement is stranger still. Imagine two particles, born from the same quantum event, their fates forever intertwined. They fly apart, separated by miles, by light years, by the vast expanse of the cosmos. And yet, they remain connected by an invisible, instantaneous thread. This is quantum entanglement, a phenomenon so bizarre that Einstein famously called it spooky action at a distance. Entanglement means that two particles, no matter how far apart, are no longer independent entities, but are part of a single, unified quantum system. If you measure a property of one particle, say its spin, and find it to be clockwise, you instantly know, with absolute certainty, that its entangled partner, on the other side of the galaxy, will be found to be counterclockwise if you were to measure it. This instantaneous correlation seems to defy one of the most fundamental principles of physics, that no information can travel faster than the speed of light. Einstein was convinced that this spooky action was a sign that quantum mechanics was an incomplete theory. He believed that there must be some hidden variables, some unseen, predetermined properties of the particles that were secretly guiding their behavior. The particles, in his view, were like a pair of gloves, separated into two boxes. The moment you open one box and find a left-handed glove, you instantly know the other contains a right-handed one, not because of some spooky, faster-than-light communication, but because their states were determined from the very beginning. For decades, this was a philosophical debate. But in 1964, the physicist John Bell devised a brilliant mathematical theorem that transformed this debate into an experimental question. Bell's theorem established a set of inequalities that would have to be satisfied if any local hidden variable theory, like Einstein's, were correct. Quantum mechanics, on the other hand, predicted a clear violation of these inequalities. The stage was set for a definitive test of the nature of reality. And when the experiments were finally performed, with increasing precision over the decades, the results were undeniable. Bell's inequality was violated, time and time again. The universe is not locally real. The spooky action is real. The predictions of quantum mechanics, in all their strange and beautiful glory, were confirmed. This revelation was profound. It meant that at its core, the universe is not governed by the rigid, deterministic laws of classical physics, but by the strange, probabilistic, and deeply non-local rules of the quantum world. A particle's properties are not fixed until they are measured, and once measured, entangled particles seem to communicate their states instantaneously, in a way that defies our classical understanding of space itself. And it is this very spookiness, this non-local connection, that provides the key to one of the most revolutionary concepts in all of science: quantum teleportation. Teleportation is not about physically moving an object from one place to another. It is about transferring its quantum state, the very essence of its identity, the complete informational blueprint that describes its properties, without sending the object itself. And to do this, we must use the strange and powerful magic of entanglement. The process of quantum teleportation is a delicate and beautiful dance of quantum principles. It is a process that seems, at first glance, to be a paradox, a violation of the very laws it relies on. But upon closer inspection, it is a stunning testament to the strange and beautiful logic of the quantum world. The process begins with an essential ingredient, a pair of entangled particles. Let's call them particle A and particle B. These two particles are created in such a way that their quantum states are perfectly correlated. One of these particles, A, is kept at the sender's location. The other, B, is sent to the receiver, who may be light years away. Now, a third particle, let's call it particle C, is introduced. This is the particle whose quantum state we want to teleport. Particle C is brought into contact with the sender's entangled particle, A, and a special joint measurement is performed on them. This measurement, known as a Bell state measurement, does something remarkable. It forces the combined system of A and C into one of four possible entangled states, and in doing so, it has a profound and seemingly destructive consequence. The original quantum state of particle C is completely erased. It no longer exists at the sender's location, but the information has not been lost. It has, in a sense, been imprinted onto the distant, entangled particle, B. At this moment, the receiver's particle, B, has absorbed the quantum information from particle C, but it remains in a scrambled, incomplete form. To complete the teleportation, a final crucial step is required. The sender must communicate the result of their Bell state measurement, a simple 2-bit piece of classical information, to the receiver. This message must travel through normal space, at or below the speed of light. Once the receiver has this classical information, they know which of the four possible outcomes occurred at the sender's end, and they can perform a specific, simple transformation on their particle, B. And with that final touch, particle B becomes a perfect, identical replica of the original particle C, possessing the exact same quantum state that was destroyed at the sender's end a moment before. The teleportation is complete. The information has been transferred. But what makes this process so strange and so profound is that nothing physical has traveled between the two locations. The quantum state did not move through the intervening space. The particle at the receiver's end was never in physical contact with the original. And yet, somehow, the exact and incredibly fragile quantum information has been perfectly reconstructed, as if by magic. This raises a deep and fundamental question. Where was the information during its journey? One interpretation is that quantum states are not localized entities at all. They are non-local patterns of probability spread out across space-time. In this view, teleportation is not a process of movement in the classical sense, but is a rearrangement of this non-local information, a shifting of the quantum state from one physical carrier to another, a process that is not constrained by the normal rules of spatial separation. Another, related perspective comes from the framework of quantum field theory, which, as we have seen, suggests that particles are just excitations of an underlying universal quantum field. In this view, teleportation is not about moving a thing from point A to point B, but is an operation on the field itself, a process that causes the quantum state to demanifest at one location and re-manifest at another. Regardless of the interpretation, one thing is clear: quantum teleportation, while seemingly instantaneous at the quantum level, does not allow for faster-than-light communication. The need to transmit the classical information about the measurement outcome ensures that the overall process is always limited by the speed of light, preserving the sacred principle of causality and keeping Einstein's theory of relativity intact. But this does not make the process any less remarkable. Quantum teleportation is a direct and powerful demonstration of the deeply non-local nature of reality. It is a process that is only possible because the universe, at its core, is not a collection of separate, independent objects, but a single, holistic, and entangled system. And it is a process that has already been achieved in laboratories around the world. Scientists have successfully teleported the quantum states of photons, of atoms, and even of small molecules over increasingly large distances. The future of this technology is one of incredible promise. It is the key to building a secure, unhackable quantum internet. It is the foundation for creating large-scale, distributed quantum computers. And it is a powerful tool for probing the very nature of reality itself. But as we stand on the threshold of this new quantum informational age, we are also forced to confront some of the deepest and most unsettling questions about our own existence. If the very essence of a particle, its informational soul, can be erased and reborn elsewhere, what does that mean for our own human sense of identity, of continuity, of the self? The strange magic of quantum teleportation is not just a technological trick. It is a profound and deeply philosophical challenge to our most cherished assumptions about what it means to be real. The question of whether quantum teleportation could one day be applied to a human being is one that pushes the boundaries of science, of ethics, and of philosophy. It is a question that forces us to confront the very nature of our own identity, of our consciousness, of the self. At first glance, the idea seems like the ultimate science fiction dream: to step into a machine, to be dematerialized, and to be instantaneously reconstructed on a distant planet, a perfect copy of your former self. But the quantum reality of teleportation is far stranger and far more unsettling than this simple picture would suggest. The first and most crucial thing to understand is that quantum teleportation does not transport matter. It transports information. To teleport a human being, you would not be sending their atoms across space. You would be scanning the complete quantum state of every single particle in their body, an almost infinitely complex task, destroying the original in the process, and then using that information to reconstruct a new body, atom by atom, at the destination. This is not a process of movement. It is a process of destruction and recreation. And this is where the profound and deeply troubling philosophical problems begin. The no-cloning theorem of quantum mechanics, as we have seen, states that it is impossible to create a perfect, identical copy of an unknown quantum state. This means that if you were to be teleported, there could be no backup copy of you. The original you, the one who stepped into the machine, would have to be destroyed for the new you to be created. The process is one of replacement, not duplication. So, is the person who emerges at the other end still you? From a purely physicalist or functionalist perspective, the answer might be yes. If consciousness is nothing more than a complex pattern of information, a specific arrangement of neural connections and quantum states in the brain. And if that pattern is perfectly replicated, then the subjective experience of consciousness should, in theory, continue seamlessly. The new you would have all the same memories, the same thoughts, the same feelings, the same sense of self. For them, it would be as if they had simply closed their eyes in one place and opened them in another. But this is where the thought experiment of a malfunctioning teleporter becomes so powerful and so disturbing. Imagine the machine scans you, transmits your information, and reconstructs you at the destination. But due to a glitch, it fails to destroy the original you. Now there are two of you. Both are physically identical. Both have the same memories. Up until the moment of teleportation, both believe, with absolute conviction, that they are the real you. Which one is right? Who has the claim to your life, to your relationships, to your past? This scenario highlights a deep problem with a purely functionalist view of identity. It suggests that there may be something more to the self than just a pattern of information. There is also the issue of continuity of consciousness. We have a powerful, intuitive sense that our self is a continuous, unbroken stream of experience, a single thread that runs from our birth to our death. The process of teleportation, of destruction and recreation, seems to violently sever this thread. Would the original you experience a moment of annihilation, a final, terrifying end? And would the new you just be a perfect, but ultimately soulless copy, a philosophical zombie that looks and acts just like you, but has no genuine, inner, subjective experience? Some theories of consciousness, like the orchestrated objective reduction model, suggest that this might indeed be the case. If consciousness is a real physical, a quantum process that is tied to the specific physical structure of the brain, then it may not be something that can be simply copied and pasted into a new physical substrate. The delicate quantum coherence that gives rise to our subjective experience might be a unique and non-transferable property of our original biological brain. In this view, the teleported you would be a perfect physical replica, but it would be an empty shell, a being without a soul. But even if we set aside these more exotic theories of consciousness, the very nature of time and perception in the teleportation process raises a host of unsettling questions. If the reconstruction process at the destination is delayed by 10 minutes, what does the teleported person experience? Do they exist in a state of nothingness for those 10 minutes? Or do they experience an instantaneous jump forward in time, a gap in their subjective experience that they can never account for? And what if the reconstruction process fails entirely? If the original you is destroyed, but the new you is never created? Have you died, or from your own subjective perspective, have you simply ceased to exist at a particular moment, with no experience of death at all? These are not just scientific questions. They are deep, existential riddles that touch on the very meaning of what it means to be alive, to be a person, to have an identity. If teleportation were ever to become a reality for human beings, it would force a profound, and perhaps painful, reevaluation of our most deeply held beliefs about the self. It could lead to a new and more fluid understanding of identity, where the self is not a fixed, singular entity, but a pattern that can be moved, that can be stored, that can perhaps even be branched. It could open up the possibility of a new kind of immortality, where our minds are not tied to a single, fragile, biological body, but can be backed up, transferred, and restored. But it would also open up a Pandora's box of new and deeply challenging ethical and social dilemmas. The question of teleportation is not just about whether we can do it. It is about whether we should. And it is a question that forces us to confront the possibility that our cherished and seemingly solid sense of a continuous, singular self is just a fragile and beautiful illusion. An illusion that the strange and powerful magic of quantum teleportation threatens to expose. The paradox of a malfunctioning teleporter, the scenario where an original and a copy of a person coexist, leads us down a rabbit hole of even deeper and more mind-bending quantum possibilities. It forces us to confront the idea of quantum immortality, a strange and unsettling consequence of the many worlds interpretation of quantum mechanics. In the many worlds view, as we have seen, every quantum event causes the universe to split into multiple parallel branches, with each branch corresponding to a different possible outcome. If a teleportation machine has even a minuscule 1 in a trillion chance of malfunctioning and failing to destroy the original, then in the vast branching tree of the multiverse, there must be a branch where this failure occurs. From an external, the third-person perspective, the vast majority of teleportation events are successful. The original is destroyed, the copy is created, and the process works as intended. But what about from the first-person, subjective perspective of the person stepping into the machine? This is where the idea of quantum immortality comes in. The theory suggests that your consciousness, your subjective stream of experience, will always and only follow the branches of the multiverse where you survive. You can never, by definition, experience a reality in which you have ceased to exist. So, if there is a branch of reality where the teleporter malfunctions and the original you is not destroyed, then your consciousness must, according to this theory, follow that branch. From your perspective, you would step into the teleporter. The machine would whir and hum, and then nothing would happen. You would emerge, unscathed, to be told by a surprised scientist that the teleportation had failed, but that a perfect copy of you had, in fact, been created at the destination. For the rest of the world, there are now 2 of you. But for you, the original, your stream of consciousness has remained unbroken. This has a truly bizarre and deeply unsettling implication. It suggests that from your own subjective point of view, you can never die in a teleportation event. You will only ever experience the realities in which you survive. It is a form of personal, probabilistic immortality. This idea can be extended beyond teleportation to any life-threatening event. If you are in a car crash and there is even a tiny, non-zero quantum probability that you will swerve at just the right moment to survive, then, in the many worlds picture, there is a branch of reality where you do, and your consciousness will follow that branch. Everyone in the other branches will mourn your tragic death, but you will experience a miraculous and seemingly impossible escape. Over the course of a long life, a person who believes in quantum immortality would find themselves living a charmed and increasingly improbable existence, surviving against all odds, a living testament to the fact that their consciousness is always and only on the winning side of the cosmic quantum coin toss. This is a strange and deeply counterintuitive idea, and it is one that is, of course, highly speculative and untestable. But it is a logical consequence of taking the many worlds interpretation of quantum mechanics seriously. And it completely reframes our understanding of what teleportation would mean for the self. It would not be a simple process of movement from A to B. It would be a process of branching, of creating new versions of reality. Every time you step into a teleporter, you are not just traveling. You are playing a game of quantum Russian roulette, a game in which, from your own perspective, you can never lose. But what does this do to our sense of identity? If there are an infinite number of yous branching off with every quantum event, which one is the real you? The many worlds interpretation suggests that they are all equally real. Identity is not a single, continuous thread, but a vast and ever-growing, branching tree. This is a vision of the self that is far more fluid, more multiplicitous, and more deeply connected to the probabilistic nature of the cosmos than our classical intuition would ever allow. The implications for human society would be profound. How would our legal systems deal with the existence of multiple identical copies of a person who would be responsible for the actions of a branched self? How would our concepts of love, of family, of inheritance be transformed in a world where identity is no longer singular? The psychological impact would be equally staggering. Would the knowledge that you are constantly branching into other realities lead to a sense of existential liberation, or to a profound and dizzying sense of personal dissolution? Would people embrace the fluid, branching nature of the self, or would they cling, with even greater desperation, to the illusion of a single, stable identity? And what about the ethics of teleportation itself? If every use of a teleporter creates a new branch of reality, are we, in a sense, polluting the multiverse with an endless proliferation of copies? These are questions that are on the very frontier of our scientific, philosophical, and ethical thinking. They are questions that are born from the strange and beautiful marriage of our most advanced physical theories with our deepest and most enduring questions about the nature of the self. Quantum teleportation, in this light, is not just a technological dream. It is a philosophical mirror, a tool that reflects back to us the deep and often unsettling quantum nature of our own human existence. It forces us to confront the possibility that we are not the solid, singular, and continuous beings we believe ourselves to be, but are something far stranger, more fluid, and more wonderfully mysterious, a branching, probabilistic, and perhaps even immortal wave of consciousness, forever surfing the crest of an infinite quantum sea. The strange and powerful phenomenon of quantum teleportation does not just challenge our understanding of space, it also, and perhaps even more profoundly, challenges our understanding of time, our classical. Everyday intuition tells us that time is a one-way street, a river that flows inexorably from a fixed past, through a fleeting present, to an open future. But the quantum world, with its non-local connections and its probabilistic nature, seems to hint at a more complex and more mysterious temporal reality. And quantum teleportation may be the key that allows us to unlock its secrets. At its core, teleportation is about the transfer of quantum information, and this information, as encoded in the state of an entangled system, seems to exist outside the normal constraints of space. The connection between two entangled particles is instantaneous, regardless of the distance between them. But if this connection can transcend space, could it also transcend time? Could quantum teleportation be used not just to send a message across the galaxy, but also to send a message back to yesterday? This is a radical and deeply challenging idea, but it is one that is not entirely ruled out by the laws of quantum mechanics. The equations of quantum mechanics are, for the most part, time-symmetric. They work just as well for a process running backwards in time as they do for one running forwards. This has led some physicists to speculate that the non-local connection of entanglement may not just be a spatial one, but a temporal one as well. Two particles could be entangled in time, with a measurement on a particle in the future having an instantaneous effect on the state of a particle in the past. The famous delayed choice quantum eraser experiment is a stunning and deeply perplexing demonstration of this kind of apparent backward-in-time influence. In this experiment, the choice of whether or not to measure the which path information of a photon seems to retroactively determine whether that photon behaved as a particle or a wave in the past. It is as if a decision made in the present can reach back and change the nature of a past event. This does not mean that we can send a controllable message back in time to change history. But it does suggest that the relationship between the past, the present, and the future at the quantum level is far more subtle, more holistic, and more mysterious than our classical intuition would ever allow. Could quantum teleportation be used to harness this strange temporal non-locality? Imagine a scenario involving entanglement swapping. You can take two independent pairs of entangled particles, and by performing a specific joint measurement on one particle from each pair, you can swap the entanglement so that the two previously unconnected particles from the different pairs become entangled with each other. Now, what if one of these entangled pairs was created in the distant past, and the other is created in the present? By performing an entanglement swap, you could, in theory, create an entangled link between a particle that exists now and a particle that existed then. You would have created a quantum channel that connects two different points in time. Could this channel be used to teleport a quantum state from the present to the past? This is a highly speculative and technically challenging idea, but it is one that is being seriously explored by some theoretical physicists. And it opens up the breathtaking possibility of a new kind of time travel. A time travel not of physical objects, but of pure quantum information. This would be a form of time travel that could potentially bypass some of the famous paradoxes of classical physical time travel. You could not go back and kill your own grandfather because you cannot teleport a macroscopic object. But you might be able to send a single qubit of information back, a quantum message that could perhaps influence the probabilities of past events. But even if such a process were possible, the universe may have its own built-in chronology protection mechanisms. The self-consistency principle, proposed by physicists like Igor Novikov, suggests that even if time travel is possible, the laws of physics will conspire to prevent any paradoxes from occurring. Any action you take in the past will be, in a sense, self-consistent. If you were to send a message back in time to warn yourself not to step into the street and get hit by a bus, something would have to happen to prevent you from receiving or acting on that message. The bus would still hit you. The outcome would be consistent with the fact that you were there, in the future, to send the message in the first place. The many worlds interpretation of quantum mechanics offers another, and perhaps more elegant, solution. If you were to send a quantum state back in time, you would not be sending it back into the past of your own universe. You would be sending it to a different parallel branch of the multiverse. You could change the past in that universe, but it would have no effect on your own personal history. The timeline would remain consistent because you have simply created a new and different one. The deep and mysterious connection between quantum teleportation and the nature of time is a frontier of scientific inquiry that is still in its infancy. But it is a frontier that is full of profound and potentially revolutionary possibilities. It is a frontier where the strange, non-local magic of the quantum world seems to touch upon the deepest and most enduring mysteries of our own temporal existence. Is it possible that our own consciousness, with its strange and often non-linear relationship with time, is a macroscopic manifestation of these deep quantum temporal effects? Could our flashes of intuition, our moments of déjà vu, our precognitive dreams, be the result of our brains as quantum systems, tapping into the subtle temporal entanglements of the universe? These are speculative questions, to be sure, but they are questions that are no longer just the domain of the mystics and the philosophers. They are questions that are beginning to be asked in a new and more rigorous way by the physicists who are probing the very heart of quantum reality. Quantum teleportation has shown us that our classical, intuitive understanding of space is a profound illusion, and it may be that its greatest and most unsettling. Revelation is still to come that our classical, intuitive understanding of time is an illusion as well. The strange, non-local, and instantaneous nature of quantum teleportation does more than just challenge our classical notions of space and time. It forces us to confront an even more radical and more profound possibility that the universe itself is a vast, interconnected teleportation network. In this vision, space is not a fundamental, empty void that separates objects, but is an emergent illusion, a macroscopic manifestation of a deeper and more fundamental level of quantum informational connectivity. The universe is not a collection of separate things. It is a single, holistic, and entangled system, where every part is in instantaneous communication with every other part. This is an idea that has its roots in the holographic principle and the Eier-Upper conjecture, which, as we have seen, suggests that the geometry of space-time is a holographic projection of the underlying quantum entanglement between its constituent parts. In this view, the universe is not in space. Space is in the universe. The seemingly vast distances between the galaxies are not a measure of a fundamental separation, but are a reflection of the weakness of the entanglement between those distant regions. Two particles that are right next to each other are strongly entangled. Two galaxies that are billions of light-years apart are very weakly entangled, but the connection is still there. If this is the case, then quantum teleportation is not a strange, anomalous process that violates the normal rules of space. It is a direct and powerful manifestation of the true, underlying, non-local nature of reality. It is not about sending information across space. It is about accessing the hidden, informational pathways that are the very fabric of space itself. This would mean that our current and technologically challenging methods of teleportation, which rely on the creation and distribution of entangled particle pairs, are just a clumsy and very inefficient way of tapping into a universal process that is happening naturally and continuously at every point in the cosmos. This vision of a teleportation universe has the potential to shed new light on some of the deepest and most perplexing mysteries of modern astrophysics. The phenomenon of fast radio bursts, for example, is a major puzzle. These are incredibly bright and incredibly short, bursts of radio waves that seem to be coming from distant galaxies. Some of these bursts repeat with a strange and often eerie periodicity. The source of these bursts is completely unknown, and they release an immense amount of energy in a fraction of a second. Could it be that these are not astrophysical explosions in the classical sense, but are a form of natural, large-scale quantum teleportation event? A momentary, coherent collapse of the wave function of a vast number of entangled particles. A glitch in the cosmic teleportation network. The existence of ultra-high energy cosmic rays is another long-standing puzzle. These are single, subatomic particles that arrive at the Earth with an energy that is millions of times higher than anything we can produce in our most powerful particle accelerators. The problem is that these particles should not be able to travel across vast intergalactic distances without losing their energy through interactions with the cosmic microwave background radiation. And yet, we see them. Could it be that these particles are not traveling to us in the classical sense at all? Could they be teleporting from their distant sources, arriving at the Earth with their energy intact, having bypassed the long and energy-sapping journey through intergalactic space? These are, of course, highly speculative ideas, but they are a testament to the fact that the universe is full of phenomena that do not seem to fit our simple, classical, and local understanding of reality. And the idea of a universal teleportation network provides a new and potentially powerful framework for thinking about these mysteries. But the implications of a teleportation universe extend far beyond the realm of astrophysics. It has profound implications for the future of our own technological civilization. If the universe is a natural teleportation network, then the ultimate form of travel and communication may not be about building faster spacecraft or more powerful transmitters. It may be about learning to hack the code of the cosmos, to tap into the underlying quantum informational network that connects all of reality. A sufficiently advanced civilization might not need to travel through space at all. They might be able to simply relocate themselves, to teleport their matter, their energy, and perhaps even their consciousness from one point in the universe to another by manipulating the deep entanglement structure of space-time itself. This could be the ultimate explanation for the Fermi paradox, the puzzle of why we have not yet seen any evidence of other advanced extraterrestrial civilizations. Perhaps they are not traveling between the stars in physical spaceships. Perhaps they have graduated to a higher, more efficient, and more subtle form of existence. A form that is based on the direct manipulation of the quantum informational fabric of the cosmos. They are not out there to be seen. They are everywhere, woven into the very structure of reality itself. This vision of a teleportation universe is a vision that is both breathtakingly beautiful and deeply humbling. It is a vision of a cosmos that is far more interconnected, more intelligent, and more mysterious than we can yet fully comprehend. And it is a vision that places information and its strange, non-local quantum properties at the very heart of reality. The universe is not a dead, mechanical thing. It is a living, breathing, and constantly communicating quantum web. And we, as conscious, questioning beings, are not just passive observers of this web. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the network, we are the network. The quest to understand quantum teleportation is not just a quest to build a new kind of technology. It is a quest to understand the very nature of our own reality. And it is a quest that is leading us to a new and profoundly different picture of the cosmos. A picture where space is an illusion, where time is a mystery, and where the universe itself is a single, vast and beautifully interconnected quantum thought. For decades, the strange and beautiful phenomenon of quantum teleportation was a curiosity confined to the esoteric world of theoretical physics and the carefully controlled environment of the laboratory. It was a stunning demonstration of the bizarre, non-local nature of the quantum world. But its practical applications seemed to be a distant, and perhaps even unattainable, dream. But that is no longer the case. We are now living at the dawn of a new, quantum technological revolution. A revolution that is poised to take the strange magic of teleportation out of the lab and into the real world. A revolution that has the potential to reshape our society, our economy, and our very understanding of information itself. The most immediate and most transformative application of this new technology is in the field of quantum communication. In our current classical world, all our communication, from a simple phone call to a classified government document, is fundamentally insecure. It relies on the principles of classical cryptography, which are based on the computational difficulty of solving certain mathematical problems. But these codes can, in principle, always be broken by a sufficiently powerful computer. And with the advent of quantum computers, which have the potential to solve these problems exponentially faster than any classical machine, the entire foundation of our modern digital security is under threat. Quantum teleportation, And the principles of quantum mechanics upon which it is based offer a new and fundamentally different kind of security. It is a security that is not based on computational difficulty, but on the very laws of physics themselves. The no-cloning theorem and the observer effect guarantee that any attempt to eavesdrop on a quantum communication channel will inevitably disturb the system and leave a detectable trace. This allows for the creation of unhackable communication systems, systems where the security is guaranteed by the fundamental nature of reality itself. The technology of quantum key distribution is the first practical application of these principles, and China, with its ambitious and highly successful MICIUS satellite program, has already demonstrated the feasibility of creating a global quantum-secure communication network. In 2017, Chinese scientists successfully teleported the quantum state of a photon from a ground station in Tibet to the MICIUS satellite in orbit, a distance of over 1,400 kilometers. It was a stunning and world record-breaking achievement, a clear demonstration that quantum teleportation is no longer just a laboratory experiment, but is a viable technology for global, secure communication. The race to build a quantum internet is now on, with governments and tech giants around the world investing billions of dollars in the research and development of the necessary technologies. A mature quantum internet would not just be a more secure version of our current internet. It would be a new kind of network, a network that can transmit not just classical bits, but fragile, quantum qubits of information. This would allow for the connection of quantum computers around the world, creating a global, distributed quantum supercomputer. The impact of such a technology on science, on medicine, on finance, on artificial intelligence would be almost impossible to overstate. This brings us to the second great technological revolution that is being powered by the principles of quantum information, quantum computing. As we have seen, a quantum computer is not just a faster version of a classical computer. It is a fundamentally different kind of machine. A machine that operates on the strange and powerful logic of the quantum world. And quantum teleportation is a crucial and enabling technology for building a large-scale, fault-tolerant quantum computer. One of the greatest challenges in quantum computing is the problem of decoherence, the tendency of the fragile quantum states of the qubits to be destroyed by their interaction with the environment. To build a powerful quantum computer, you need to be able to connect a large number of qubits together. But the more qubits you have, the more susceptible the system is to decoherence. Quantum teleportation provides a potential solution to this problem. It allows for the transfer of quantum information between different parts of a quantum computer, or even between different quantum computers in a network, without the need for a direct physical connection. You can teleport a qubit from a noisy computational part of the processor to a quiet, protected quantum memory, preserving its fragile state. You can use teleportation to create the long-range, entangled connections that are necessary for the implementation of powerful quantum error correction codes. The algorithms that will be needed to protect a quantum computation from the destructive effects of decoherence. In this sense, quantum teleportation is not just a communication protocol. It is an essential architectural component of any future large-scale quantum computer. It is the quantum wire that will allow us to build machines of unprecedented computational power. The societal and economic implications of this are staggering. A mature quantum computer could revolutionize the process of drug discovery and material science by allowing us to simulate the behavior of molecules with perfect quantum accuracy. It could transform the field of finance by solving complex optimization problems that are currently intractable. And it could supercharge the development of artificial intelligence by providing a new and far more powerful computational substrate for machine learning algorithms. But with this great promise also comes great peril. A powerful quantum computer would also be able to break most of the classical cryptographic codes that protect our current global financial and communication systems, creating a new and potentially devastating security threat. The race to develop quantum-resistant classical cryptography and to build a truly secure quantum internet is one of the most urgent and most important technological challenges of our time. The technological revolution of quantum teleportation is not just about building better computers and more secure communication networks. It is a revolution that is forcing us to confront some of the deepest and most unsettling questions about the nature of our own human existence. The possibility, however remote, of one day being able to teleport the complete quantum state of a complex biological system, or even of a human being, is a prospect that is full of both breathtaking promise and profound existential dread. As we have seen, this is not the beaming of science fiction. It is a process of destruction and recreation, and it raises a host of deep philosophical questions about the nature of identity, of consciousness, of the self. Is the person who emerges at the destination still you? Or are you just a perfect, but ultimately soulless copy? These are questions that may not have a simple scientific answer. They are questions that touch on the very meaning of what it means to be human. But even if we never teleport a human being, the very fact that the laws of physics allow for the perfect, non-local transfer of information is a profound and deeply transformative revelation. It tells us that our classical, intuitive understanding of the world, a world of separate, localized objects, is a profound illusion. The true reality is a much more interconnected, more holistic, and more mysterious quantum web. And as we learn to harness the strange and beautiful power of quantum teleportation, we are not just building a new set of technologies. We are learning to see the world and ourselves in a new and more profound light. We are moving from a worldview that is based on separation to one that is based on connection. We are moving from a reality of things to a reality of information. And we are moving from being passive observers of the cosmos to becoming its active and conscious co-creators. The journey into the age of quantum teleportation is a journey that is full of both immense promise and profound ethical challenges. It is a journey that will require not just scientific and technological ingenuity, but also a new level of philosophical wisdom, of social foresight, of human maturity. And it is a journey that is just beginning. The strange, spooky, and beautiful magic of the quantum world is no longer confined to the laboratory. It is coming into our world, and it is a world that will never be the same again. The ultimate question that the phenomenon of quantum teleportation forces us to confront is not about technology, not about communication, not even about the nature of space and time. It is a question about the very nature of reality itself. If information can be transferred from one location to another, instantaneously and without traversing the intervening space, then what does this tell us about the fundamental structure of the universe we inhabit? It suggests a reality that is far stranger, more interconnected, and more profoundly mysterious than our classical common sense intuition would ever lead us to believe. For centuries, our scientific worldview has been built on the foundation of locality, the idea that an object can only be influenced by its immediate surroundings. But quantum entanglement, the engine behind teleportation, shatters this foundation. It reveals a universe that is fundamentally non-local, a universe where the concept of distance itself may be an illusion. The two entangled particles, separated by light years, are not two separate things. They are two aspects of a single, indivisible, quantum whole. To touch one is to touch the other. This is a vision of the cosmos that is not a collection of objects in space, but is a single, vast, and interconnected quantum system. A system where space is not a fundamental, pre-existing container, but is an emergent property of the underlying quantum informational relationships between its constituent parts. This is the essence of the holographic principle. The idea that our three-dimensional reality is a projection of information encoded on a lower-dimensional surface. In this view, quantum teleportation is not a process of information traveling at all. It is a direct manipulation of this underlying holographic code, a rearrangement of the informational bits and qubits that constitute the very fabric of reality itself. This is a profound and deeply transformative shift in our understanding of the cosmos. It suggests that the true fundamental reality is not the world of matter, of energy, of space and time that we perceive with our senses. The true reality is a world of pure quantum information, a world of abstract, mathematical relationships, a world of non-local, entangled connections, and the physical universe we experience is just a shadow, a projection, a fleeting and partial manifestation of this deeper and more fundamental informational reality. This informational view of the universe has the potential to unify some of the deepest and most disparate concepts in modern physics. The mysteries of dark matter and dark energy, the puzzle of quantum gravity, the nature of time's arrow. All of these may find their ultimate explanation in a deeper and more complete understanding of the quantum informational structure of the cosmos. The universe, in this vision, is not just a physical system, it is a computational one. And we, as conscious, questioning beings, are not just passive observers of this cosmic computation. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the universe is in us. And the quest to understand the one is inseparable from the quest to understand the other. The journey into the strange and beautiful world of quantum teleportation is a journey that has taken us from the laboratory bench to the very edge of reality itself. It is a journey that has challenged our most deeply held beliefs about space, about time, about identity, about existence. And it is a journey that has left us with more questions than answers. Is our universe just one of a vast and perhaps infinite number of other parallel realities? Is the flow of time an illusion? Is consciousness a fundamental and creative aspect of the cosmos? These are questions that may not have a simple or a final answer, but they are the questions that drive us forward. The questions that fuel our relentless and beautiful human quest for knowledge and for meaning. Quantum teleportation is more than just a scientific breakthrough, it is a philosophical revelation. It is a mirror that reflects back to us the deep, strange, and wonderful mystery of our own quantum existence. And it is an invitation, a call to adventure, a challenge to see the world and ourselves, not as a collection of separate, solid, and certain things, but as a single, vast, and beautifully interconnected quantum song. A song whose notes are still being written. A song whose final and ultimate meaning we are all, together, creating.